Okay, as people trickle in, hopefully a bit faster, um, I've got a few announcements to make before we go over to the keynote. The first one is this is the last day of the conference, which is sad. Also means that all the GRCon merchandise might be, worthless tomorrow, if not sold to the right people. So we have a discount. Great deals available on tickets.radio.org. So you pre-order there, you pick up at the disc. Everyone is happy. Then the welcome desk extends its welcome to you and says, if you want to ride share to the airport and don't pay the full Uber price, you might want to meet in front of the welcome desk and coordinate. Then at 1 p.m., we will have a planning next GRCon session. So if you felt like this kind of event is your thing and you want to be part of it next year in a planning matter, or we could do it in your backyard or something, do meet up at 1 p.m. We just get one of the meeting rooms and brainstorm, coordinate, and get together. So with that being said, it is an honor and a pleasure to introduce our keynote speaker, Kristina Collins, who can be heard on HF at 8 minutes after the hour on the WWV station. And since she's been around for the full week, you might have already noticed and guessed that she's part of the Luxuriant Flowing Hair Scientists Club. So give a warm hand of applause for Kristina.
But now, much better. All right. Get my timer started there. Okay, so I finally chose a title for my talk. I decided to go with one that I've used many times before, which is The Lion and the Propagation Path. I think I've given talks of this title a few times. This is a little bit of lore that comes down to me through a lineage that goes back to one professor, Howard Comfort of Haverford College, who would tell his students, from time to time you'll be asked to give public lectures well in advance, and you will know that you want to go there and you know that you want to give a talk, but you will have no idea what you want to talk about. And so at this point, if you need a title, you should call your talk The Lion in the Path, because it sounds very impressive and it's totally meaningless and commits you to nothing. Now, the organizers kindly did not request a talk or abstract from me in advance, but I wanted to go with this title to sort of note, I've been spending the past week trying to calibrate to the audience here. This is my first time at GNU RadioCon, and I noticed, over the course of the past few days, from time to time, someone in this room will say, okay, can we get a show of hands? How many ham radio operators are in the audience? And hands will go up, and they'll go, okay, that's about half. And every question that I see somebody ask that for, it's always about half. It's not the same half. So I figure anything that I talk about is going to be old hat to about 50% of you and completely new to the other 50%. And so I'm going to try and structure things so that no one is too bored and no one is too lost. But the actual point that I want to get to is building connections between the GNU Radio and ham sci communities. Phil set this up nicely with the definition of ham sci yesterday. What ham sci is it's a collection of amateur radio operators. We're basically a listserv and a set of workshops. We welcome you to join us. Who use ham radio for scientific purpose. And I've stolen some slides from Josh. I'm going to put these in at a few points to talk about some ideas for how we might build connections between these communities. So I'll begin with an introduction to the ionosphere at a very basic level for those who are not familiar with it. I'm going to tell you a story about our first big, the first big campaign that I was a part of. The first ones that happened with HamSci were the 2017 eclipse, but there was one in 2019 that I worked on for WWV. I'll talk about the first part of the personal space weather station. This was kind of the core of my dissertation work, was the Doppler receiver we call the GRAPE. And then the WWV Scientific Modulation Working Group, which I think might have some interesting potential for collaborations. And then we'll come back to the personal space weather station as it is coming together now and the extensions that we're planning to make to that network over the next 4 years with the support we've just gotten from NSF. So slide stolen from Phil. The thing to note about the ionosphere, I've got about 4 or 5 things to kind of keep track of. The first one is that, like an onion or an ogre, it has layers. The layers are mainly the E and F layers, and then there's the D region below those. So who knows where these layer names came from? Does anyone know the story? Okay, about half. So this guy Appleton in the 60s got the Nobel Prize for ionospheric modeling, and he, I think it was him, he had a chart, and he had written E on it for voltage, because voltage began with E in the old days. And he had figured out that he was getting reflections off of this ionospheric layer, so he labeled that the E layer, and then he figured out that there was actually a second layer, so he labeled that the F layer. And then he realized there was one in between, and he was in a hurry, so he wrote in F1 and F2, and then they started calling the D region the D region. And then he was like, I don't want to change it, because what if there are A, B, and C regions, and there weren't? And we're stuck with this forever now. So yeah, so now you know. But the F layers will separate at night because of photoionization. Another thing to know about the ionosphere, besides that it has layers, is that it's very complicated and it's coupled into a lot of processes. This is an image from NASA Goddard that captures some of them. Honestly, the only reason I've ever seen anybody use this image is to put it at the beginning of a geospace presentation to point out how complicated the ionosphere is, and so it is here. Okay, the other thing to know about the ionosphere is that its behavior is affected a great deal by the sun. If we want to understand the Earth-Sun system, we have to understand the sun. And the sun is a very complicated thing. If you look into the current discussions on solar cycle prediction, which are a fascinating scientific discussion of our times, and I recommend it. For those who are not thinking about this space weather all the time, it's worth knowing that there is an 11-year solar cycle. You can look in the Google search statistics and see, you know, aurora searches peak about every 11 years, things like that. How many people saw aurora during the geomagnetic storm earlier this year? Okay, about half. So this is something we can go back and we can find, you know, historically. Here's a record from the 1700s. This was an eyewitness account of red aurora in Japan. Here's one of my favorites. This is a personal theory. This is Twilight in the Wilderness by Frederick Edwin Church. And it was painted, well, it was exhibited in 1860. Does anybody know what happened in 1859? Okay, about half. The Carrington event of 1859, which was this coronal mass ejection that induced currents in telegraph lines, so that telegraphers worked out that they could send messages without a battery connected. It would be very bad if one hit us now. We came very close in 2012. But that sort of is the 100-year flood of space weather. And the curators at CMA think that he put all of these vivid colors in this painting because he was saying something important about the Civil War. I think he put them in there because he had seen aurora and it had changed his notions of what a sky could be. Plus, he drew it out in the field and then finished it in his studio in New York, so maybe he was feeling a little liberal about it, who knows. All right, and then the other thing to retain about space weather, and Phil again talked about this yesterday, is that it's expensive. It was worth $100 million to SpaceX when they launched all of their satellites directly into a geomagnetic storm in February 22. And This is a fun one because in the literature, every time there is a storm, people will write papers where they'll use it as an example. And this was, I think, in one paper as the SpaceX storm before, when I would go to conferences, like, I guess the lawyers must have descended because people then started saying things like, the February 2022 geomagnetic storm which destroyed many satellites of a company that shall remain nameless. But as Phil pointed out, this was his image from yesterday. Here's a lot of Starlink satellites currently in orbit. And if this is something that you find intriguing, I can assure you it will only get more interesting and not less in the years to come. And the final thing I want people to really remember about the ionosphere, and this is maybe the most important to this crowd, is that it's an undersampled system. This is a total electron content image, and I'm not going to talk about anything relating to this sort of measurement today, but what I want you to notice is that, here's a day of data, and it's, every 10-minute cadence, and each of these pixels is like a degree latitude by a degree longitude. So what we can do as designers of instruments and open source hardware and software is build systems that can fill in some of the missing pixels on maps like this and get some better idea of what's going on. So for the purposes of this talk, we're going to use a very simplified model of the ionosphere, like at about the level when people were first thinking about it a century ago. Marconi had claimed success in getting a message across the Atlantic, and there were two different guys, Kennelly, who was a physicist working in the United States, and Oliver Heaviside, who was an engineer in England. And they both came up with this concept at the same time that, the radio waves really ought to just go right out into space, because the curvature of the Earth and so forth. So they must be bouncing off of something. And they both said, well, I bet that something is a layer of ionized gas. And they wrote it down and within, weeks of each other. And so that's known as the Kennelly-Heaviside layer, sometimes just the Heaviside layer. How many people here are fans of the musical Cats? Okay, about half. You know where it's going. So yeah, when they say up to the Heaviside layer, they're talking about the ionosphere. Fun fact. And this is also where ham radio operators come in. This, on the right here, is the January 1922 issue of QST, which is published by the American Radio Relay League, which the ARRL is a big ham radio organization, published to this day. And this was the first ham radio contest. The first bit of radio sport was the transatlantic test. They had stations in the United States send signals, and they were picked up by a station in Scotland. So this is a science campaign. This goes all the way back to the beginning of the hobby. And now we have, radio sport, we have capture the flag, we have all of these things that have a heritage of being a gamification of what we already need to do for scientific purpose. So it makes a lot of sense for HamSci to then come in and say, all right, well, let's return to those roots and start using ham radio for science in a concerted way. You already pretty much know what ham radio is, but the thing that we like to say about it is that it's the national parks of the electromagnetic spectrum. It's certain provinces where you are permitted to go and participate in activities that support, fun and recreation, international goodwill, and technical achievement. And as long as you clean up the trash and you don't have spatter off the edge of the band and don't crash anything that you shouldn't, then you're allowed to be there and you're allowed to participate in things, and there's many different ones that are worth going to try. So I want to say a word here about also what makes citizen science, because there's some definitions of this that are becoming more rigorous on the science side. On the right here, I have this article I wrote for EOS, which is the magazine of the American Geophysical Union, and it's been carried by QST in a lot of publications. My favorite thing was that they took this article and transmitted it as part of the shortwave radiogram, so I could put it in FL Digi and watch it print out. So that was a lot of fun. But when I wrote this, I used the word citizen science, and the editors were like, we're not sure. We want you to use crowdsourced science. because there's a distinction drawn now between citizen science, crowdsourced science, community science. In community science, that's something where you have a population that has a concern, usually a public health concern, about something, and they're seeking out scientific aid to investigate that public health concern. So, for instance, if you're looking to get lead testing in your area, for example, and you want to do a public health study in your area, that's community science. Crowdsourced science is something like Zooniverse or something like that, where you're contributing to a training data set. And the goal is to drive things through this progression to what's called co-designed science. So real citizen science should be something where the volunteers are part of the process at, about the same level as the folks who are coming in with real training and background. The volunteers should be active participants to the point of working on the hypotheses and the formulation of experiments. And that's the direction that these things are going, and everybody should be given credit for their work as well. That's also very important, because you don't want something where people are just asking for someone to go in and count things and working for free and not actually understanding what they're working on. That's not really participatory. And this is something where, amateur radio, I think, is very well positioned to build towards this. You have to scaffold toward it to make sure that there's resources explaining what you do. We already kind of have that. Little shout out to my home club, the Case Amateur Radio Club at Case Western Reserve, W8EDU. Our first paper about amateur radio was this paper in 2017. We taught a writing class with it. So for the educators in the room, if you are looking at different classes, don't just limit yourself to DSP, right? We used this as a way to talk about constrained communication, communication at a distance, censorship, technical education. There's lots of interesting angles to be taken. And what we found in putting this together was that this was a way for us to become legible to the university. If you have a college radio club, and I won't belabor this point too much for the folks who aren't dealing with this sort of thing right now, but it's hard to maintain roof access. And it's hard to, get the university to understand the resource that it represents. But if you can integrate it, as we have done, into curriculum and research and recreation, extracurricular stuff, then it becomes much clearer what it's about, and it also helps push things in interesting directions. We have used the Ham Radio Club at Case as a curricular lab for 8 different courses, many of which are core to the electrical engineering curriculum. So happy to talk about that if anybody wants to. And so this put us in the position to host HamSci 2019, which was where a lot of the ideas that I'm going to show you here came together about WWV. There's Phil with our faculty advisor, David Kasdan, 88Y. And, this is where I think one of the GNU Radio strategic plan aspects comes in, which is this concept of spreading it to increase the footprint in educational programs. I want to encourage folks to think about ways that you can extend GNU Radio into the amateur radio community and vice versa, whether that be getting your license if you haven't yet, or maybe if anybody wants to set up a table at Hamvention with us at the HamSci Collegiate Amateur Radio Initiative booth, things like that. Youth on the Air. There's a lot of ways to make the ham radio community aware of GNU Radio as a resource that they can use and contribute to. So in the interest of building up to these the system I'm going to talk about, we had several campaigns. I'm going to talk about the first one, the Festival of Frequency Measurement. Most of these were around eclipses. But this one's kind of a fun story. So first, let's talk a little bit about WWV. How many people know what WWV is? Oh, good. That actually might be more than half. Yeah, this is the heartbeat of the ham radio spectrum. You turn to 10.00000 megahertz, and you'll hear, at the tone, the time will be. WWV, all the time, all the time. So there's WWVB, which is the transmitter that runs your atomic clock, if you have a radio-controlled clock at home. There's also WWVH, which is the sister station in Kauai. It has the same carrier frequency and similar sideband modulations, but it's a little bit different. So time standards in general. There's 2 basic questions for a time standard, right? You have, how do you measure the time, and how do you disseminate that measurement? So here's some fun ways of, we've got some sundials here. You've got a courting candle. So if somebody is is coming to visit, you can adjust how long it will take the candle to burn down based on how long you want them to be there. This is one of my favorites. This is a meridian cannon. It focuses the light on this wick, and then the cannon goes off at noon. So it's safe to operate in Cleveland. There's no sun. And then disseminating measurements. So we're now at the point where we have these radio-controlled clocks, and then it's a different system, but this is the Primex clock in my old living room during daylight saving. It can only go forward, so to fall back, it has to go around 11 times. Okay. So really what this is all about is I really want to tell you guys about the Dombey Affair of 1793. But we're going to go back to the forming of the United States and how NIST came about from this. So 1788, we ratified the Constitution. It has Article 8. Article 8 says we need to have a Department of Commerce, and that Department of Commerce is going to be responsible for, among other things, weight and measures. And this makes a lot of sense, you know, as a thing for a nation to do, because the first time that any two cultures meet, they're either going to do it in commerce or they're going to do it in war. And there was a dichotomy of views among the colonies about things like how big a bushel was. So you could make, you know, good money doing arbitrage between two different adjacent states that had different opinions about how much a bushel should be. And Jefferson was somebody who was very interested in standardizing this. So in 1790, he wrote the Jefferson Report, and he had the first American standard for time, which was this pendulum simulation that you see up in the upper right, where you have a particular length of rod, and you check to see the period of that as a pendulum, and you say, okay, well, that's about a second. The issue, of course, is that in order to do that, you need to have a standard for length. So in around that time, he writes his friend Joseph Dombey in France, and he says, hey, can you come to the United States, and can you bring me a kilogram and a meter stick that are in line with the French standard so that we can standardize about it? And Dombey says, sure, yeah, you know, the French Revolution is happening, and I'd rather not be here for that in person. So better? Good, thank you. So he gets on a boat and he brings the, yeah, we'll just do this. He brings the kilogram and the meter stick, and on the way, the boat is captured by pirates. It was a very sad story, actually. Dombey died in prison. But the pirates took the kilogram and they took the meter stick. And that is how close we came to being a metric nation. It might be the most expensive thing that has ever happened. Anyway, so after that, it took us like a while to get it together. So it wasn't until 1838 that Congress actually officially adopted a common system of weight and measure. And then it wasn't until 1900 that they found the Bureau of Standards, which today is known as NIST. So, okay, let's get to the part where radio comes in. So one of the first things they did, 1919, is the point when they announced award the call sign for WWV, the standard station for the United States used to disseminate time. And they were, you know, putting various signals on this. I just love this quote. This is a snippet from an internal newsletter. This was when WWV was in Gaithersburg, or not Gaithersburg, in DC. It was actually in the building that is the visitor center for NASA Goddard now. And essentially what they're saying here is like, oh, we figured out that you could put music on this, and then you could listen to music, but far away from the music. And it was nice. You know, a fellow could have a nice evening that way. So really early days of radio here. And this was, I think, the first clockwork setup here, and they've improved over the years. I had an opportunity last year to see the clock in Boulder, the cesium fountain that is the time standard, and also to see the strontium system that they're going to transition to. And that line will keep going. We're down to 1 part in 10 to the 18th, which is very exciting. So, okay, here's the part of this where the story gets kind of fun for me. 2018, there was a proposal to defund WWV and WWVH. And this was something where within the ham radio community, people picked up on this. And I remember the ham sci mailing list, there was a discussion where 3 or 4 people came in, they were like, wow, I'm using this for 7 different things, but I can't really think of a good reason to keep it. So I guess it's just going to disappear. And I wrote a blog post on our website with, you know, here's who you should call in Congress and annoy, and here's what you should say in order to annoy them. And this got picked up in some kind of surprising places. It showed up in a bunch of blogs. It showed up in other ham radio magazines and websites. I don't think that we were what tipped the scale by any means. I think this was like many things in radio. The Navy needed it for something, you know, and I'll never know what it was. But in any event, they did end up keeping it, and because we had been part of this whole effort and been in touch with people, we got to go to the party. And this was the centennial party that was held on actually the day they would have defunded it, which was also the 100th anniversary of the awarding of that call sign. And so we had a ham radio contest, and brought all these people together and sent out special certificates. And one of our goals was to use this as a way to justify WWV as a scientific resource. So we ran this campaign called the Festival of Frequency Measurement, where people would measure the Doppler shift of the carrier. And you can see, you know, here's some stations on the west side of the country and some on the east side of the country, and they're seeing, you know, regionally similar pictures. And so this was a good and promising result of this, this distributed method. Now, the reason we were able to do this is because of a contest that already exists called the Frequency Measuring Test, which is just what it says on the tin. And this motivated somebody to put this into FL Digi so that you can go into the waterfall and you can click a carrier, and it will estimate where that carrier is over time, and then it spits out this, this nice CSV file. And this was the foundation of our research for like 5 years, was this little, this aspect of this piece of software. Another slide stolen from Phil here. I want to direct your attention to Bright and Tuva, who are the two dudes on the left side. And figure 9 at the top here, this is from their Nature paper in 1926. Note the radio station that they're using. That paper is entitled On the Existence of the Conducting Layer, I think, something like that. It's very early on in ionospheric physics. So we're really doing the same types of measurements that they were doing. Okay, so what do we got that they ain't got? And the answer is Raspberry Pis, GPS-disciplined oscillators, the internet, open source software, the ability to take many different stations and use them all as one coherent meta-instrument that's all looking at the same thing. So really what has changed most of all, apart from, you know, some of the technical details are a little different, but what really is new is the idea of cooperation. A little bit about the frequency measuring test. So simplified model of Doppler shift. This is all models are wrong, but some are useful time. So the sun rises, photoionization occurs, what we call the virtual height of the ionosphere. So if we imagine it as just a mirror, and it isn't, but if we imagine it as just a simple reflecting layer like Heaviside might have thought of it, then that goes down during the day, right? And those wavelengths, the wave fronts of our signal, which is at leaving WWV on the left at 10.0000000 megahertz, those wavefronts get scrunched and it arrives at our receiver at W880U as a slightly higher frequency while that change is happening. Evening comes, the process reverses, the wavefronts get stretched further apart as the virtual height rises. You end up with something that looks like this. So you have a pretty typical shape here where there's a sunrise peak in the middle of the day, and then you can kind of capture traveling ionospheric disturbances, which are these waves that go through the bottom side of the ionosphere. And you know, when you have enough stations, you can start to build something of a picture of them. So it's a blind men and the elephant situation where we are looking at different aspects of the, you know, looking at the situation from different angles. You can't get all of this information from one station. You have to have multiple ones. And the more you have, the better. And the greater density you have, the better. And so this is a wonderful thing for ham radio operators to do because there's utility to having many stations out there. Okay, so the first part of the low-cost personal space weather station is, this is our system here. If you're curious, there's a link in the top right. That DOI will take you to the paper that describes all of it. So I won't go into too much detail about the hardware. In fact, I'm just going to skip through all of this. All you need to know is that it's a low IF receiver. And we call it the grape because it's easier to say than low-cost personal space weather station because people like to name electronics after tiny fruit. You know, you got your lime SDR, your kiwi SDR, you get the idea. And it does its best work in bunches. Uh, and the other thing that people insisted I add was that we hope the data will ferment into something quite nice. And I gotta tell you, it has. After going through 5 years of cataloging Doppler flashes from solar flares that we never expected to see in the data. So at the time that I put this together, we've got over 100 stations. Support for this is provided entirely by volunteers. The volunteers do absolutely participate in the engineering side of it. Here's a 3D printed case for it that some guy just made. We use it now. It's great. Here's what we had from yesterday. This is a little bit active because we're in a very active period right now. We just coming out of a G4 storm, I believe. If you look at, this is 24 hours of data. Each of these lines is put together as one of the stations in the New England grape cluster. I think there might be one outlier in British Columbia. And these plots appear in my email inbox every night at 9 o'clock. They are prepared by a group of ham radio operators, and it's my favorite thing. And I look at them and I look for the solar flares, and that's what I do instead of Wordle. So what's happening here is, one of the most interesting parts to me. At about 15:30, you see how there's all of those stations, there's a peak with all of them lined up. Pretty sure that was a solar flare. So I will take a look at that, and then I take a look at space weather and confirm there. So we got an NSF grant to measure the 2023 and 2024 solar eclipses with these and to install a bunch of them in order to do so. And the thing about an eclipse is, we talked about the relationship of photoionization. An eclipse is it's the closest you come to getting a controlled experiment in space. You have this known bit of darkness, and it lends itself very well to a campaign. The history of eclipse science is a very interesting one. For us, it was an excuse to put together a lot of stations. These are the volunteers who did that. Bill Blackwell in the second photo is the one who puts together those plots. And these guys built the more advanced version of the grape, which is listening for audio and captures the sidebands as well as the carrier. This is still a narrowband receiver. We'll come back to that. Here's another couple plots from the New England Grape Group about the eclipses. We've been chasing these S-curves for many years. This was the annular eclipse in October. Here was the eclipse in April. I didn't even bother boxing it because it's obvious, I think, where it is between 1800 and 20. So it's the night-day cycle in miniature. And you can see that it sort of, if we had mapped these by longitude, you could see very easily where it sort of has slid across the country. So it was nice to get that, and we had a nice quiet day in space weather that day. Because we have many stations, we can look at events coming from above and below the ionosphere. This is the wonderful thing about it, is that it has all of that coupling. And so you can, it picks up on these things. And so we have on the left, there's a couple instances of solar flares. There's an X1 class solar flare and a C4.9 class. There are some advantages this has over super darn radars. We have a 1 second cadence, which is very nice. And the spatial distribution, the low cost, etc. And then on the right, this was from the Tonga eruption in January of 2022. And you can see the Lamb wave, which went all the way around the planet, showed up in our data as well. Data collection process, basically we put it on an FTP server. Again, there's a paper describing all this. Here's example data from one station. This is our pilot node. And the plots on the right are each of those lines of pixels from 0 to 24 hours. That's 1 day, right? And it's color mapped. The top one's according to red-blue for Doppler shift. And so you can see the change in length of day over the course of a couple of years that way, and you can look at long-term variability. For anybody who might be colorblind, here's an alternative color map for those images. The part where in the lower plot, which is power, what's happening there at that line is that he swapped out his antenna for a less noisy one, so everything becomes a little bit clearer, and it's nice to be able to see those sorts of things. All right, so at this point we've got these receivers. They're narrow band. They're almost all looking just at the carrier, really. So what else can we get out of our time standard stations? WWV is a fantastic resource because we don't have to maintain it. It's very loud. It's got this very precise carrier. But there's other things that we want to explore because, again, our model is not really accurate to everything that's going on. We usually will have multipath. We have refraction in the ionosphere. It's a more complicated story than just the carrier would lead you to believe. And there are these different elements of the modulation that can be used for different things. You've got the carrier signal that we've been using, but you can also look at the second ticks. Time of flight is a fantastic thing to know if you're trying to actually build a model of things. The carrier is actually not a great, great observable. So we were looking at some of the different ways that we could use these. And we were also in conversation with folks at NIST about what we might add to make it more useful for scientific purpose. So for a couple of years now, I've been running the NIST Scientific Modulation Working Group for WWV and WWVH, and this is our signal that plays at 8 minutes past the hour. Whoops. I don't know if there's a way to turn this up. Perhaps not. Well, you can see it in the spectrum anyway. That's the voice announcement. Pseudo-random code. Here's the phase coherent tones. This is for testing the linearity of the transmitters. Chirps. I always like that part. And then we have just a single impulse, and then the same pseudo-random code again, so that you can compare them. So I think that this, going back to, how does this fit into the priorities for GNU Radio? We have a number of projects. This is one of them where I think GNU Radio can be very helpful for analyzing some of these things. Most of what we do, we just shelve our data. We don't have real-time stuff. And we'd like to get more real-time stuff, and we'd like for that software to be, durable and manageable. We can certainly use help with that. Another thing that I think is worth pursuing is using these time standard stations as test signals. They're very accessible. I think that anything that makes sure that they're useful and can demonstrate that they're useful is a good thing for keeping them around. And you can incorporate them into educational activities, have people go and measure one of these signals, and then integrate that into whatever flow graph you might be working on that day. There's many aspects of the modulation as shown that can be used for different things. So there's a couple of DOIs on here to access the code that's used to generate that signal and things like that. And then we have, analysis of eclipse data. The GRAPE 2, as it was called, that one that I showed all of them lined up that measures the sidebands, that collects everything in digital RF format as well. So we will be working on a workflow for analysis that will hopefully be compatible as time goes on. All right, so now we get into the next steps for the PSWS, and here's where we finally get to some proper SDRs. I've stolen these slides from Nathaniel, so hopefully I can do them reasonable justice. So at this point in the story, right, we have these passive receivers, and they're narrow band, and we can do some things to give them some more stuff to look at, but we're still only looking at 2.5, 5, 10, 15 megahertz. We're not getting the full picture. And what we'd really like is something that's like, more like a Kiwi SDR, but more scientifically usable. Essentially what we would like is a USRP, but cheaper. And so this was the goal that we set out with the original vision for the personal space weather station. So initially we worked with Tapper on putting together what they called the Tangerine SDR. It's been a valiant effort, but they were not able to keep pace with turnover of FPGAs. So while that was going on, our friend Phil Karn of KA9Q Radio, developed his software further, and we worked out that was capable of doing pretty much the things that we needed it to do, of creating these arbitrary slices so that you could have virtual receivers from the raw IQ data. And the RX888 turns out to be at about there we go, yes, thank you. Please direct your attention. Yeah. The RX888 turns out to be the right size and price and capabilities for a lot of what we want to do. So this has been prototyped, and I'm going to show you a couple of examples. Rob Robinette AI6VN has been a lead on this part of the project, and here's some of the things that we wanted to accomplish with it. Basically to have something that fits into the network we currently have while also really increasing its capacities. The other nice thing about this too is, we started collecting in 2019, right? And the network has continued to grow pretty much organically of the grape receivers. The interesting thing about that is that a solar cycle is about 11 years, and it would be really great to get, data that spans a solar cycle or two, so that we can get good points of comparison that way. So we don't want anything that, diminishes our legacy data, as you might call it. We want something that fits in with it where we can integrate the analysis. And one nice thing about this that I really appreciate is that, especially for that solar flare study that I mentioned, we can go in and generate grape-like data from it. Let's see. So then the other thing about it, using Whisper Daemon, at this point, when we've added these SDRs in, it's still a passive network, right? We now have our narrowband piece and our wideband piece. And we can get a lot of information out of looking at Whisper and out of looking at sort of the aggregate of existing ham radio contacts. One of the things that happened in 2017 was there was a contest for the Eclipse, and Nathaniel and some other members of HamSci did the statistics on reverse beacon network and PSK reporter and other things where people, collect records of ham radio transmissions, and every time you have a record of a ham radio transmission from point A to point B, it means that there was a path there. So if you look at this over the course of a day and you have these, millions and millions of records, you can start to build a little bit of a picture from that, just from people going about their business as ham radio operators who want to talk to each other and see how far their reach of their station is. So this would fit very neatly into that system as well, and then we can continue to use that part of our analysis pipeline. And so here's what a complete receive station looks like. I'm going to show you a couple of examples for Nathaniel's station, which is in Scranton, Pennsylvania. Here's the annular eclipse in October 2023. So I showed you that line graph with all of those lines from the Grape Run receivers. And so this is a much more interesting thing, right? To be able to see the proper spectrum, you get a lot more data. But then you also have all of the frequencies in one place. And you have WWV, you also have the Canadian standard station CHU. So in these, there's some dotted lines, right? The one that is sort of the longer dotted line coming up from the bottom of the plot, that's the measure of solar zenith angle. And then the one that is like a V that's superimposed over that, that's the solar eclipse. So you can see how the different frequencies responded differently. And then we also have the CHU data. So compared to that little line, it's like this whole network is putting its glasses on. We're going to be able to see so much more for any given station using this hardware. And then to top it off, we also have VLF receivers. This is an example of a plot. This is just looking at man-made signals. But they can also pick up whistlers and interesting, natural VLF signals as well. And then we can get more data about our traveling ionospheric disturbances and things that we're curious about. And I don't know yet everything that we'll be using the data for, which is very exciting. I think that once people can get a chance to actually, look through their microscope, then they'll come up with ideas for more things to look at. But at this point, we still want to get in some sort of active component. Phil addressed yesterday the concept of having the combinatorial number of propagation paths. How many transmitters do you have? How many receivers do you have? You do a lot better if you can add in some transmitters. And so enter the Whisper Sonde, developed by Paul Elliott, WB6CXC. And this is documented at the Turn Island Systems page. Here's some examples of it in action, where we have a couple of different stations that are looking at the Whisper transmissions. Gwen Griffiths has done a bunch of work on this, and I recommend the presentation that's linked at the bottom. All of the HamSci stuff just got posted to YouTube in 2024. I'm going to skip some of these for time because I'm running a little bit short. So as of May, here's what this looks like. We've got some whisper-son transceivers that have been deployed. And we also have the ham-sci ground magnetometer. The goal of the personal space weather station is to have it be just like a weather station, something that's modular, where you have a central computer and then you can add in other types of instrumentation later. You know, not every weather station needs a rain gauge and a barometer and an anemometer, but you can add those in and take them out and have things drop in and out of the network as needed. We're trying to do something very similar here. And so that'll include magnetometers. I'm hoping for all sky cameras in the future to be something that we integrate. And all of this is going to come together at psws.hamsci.org, so watch this space. So yeah, at the time of writing, we currently have this system that we've determined works for our purposes, and we are going to be installing some whisper-sons. This one might be a little bit of an eye chart in the room here, but what I have here is a table from the grant that was just approved by NSF to deploy additional stations and support the ongoing development of the personal space weather station. So we're going to be deploying 30 VLF receivers across the country. We're going to be deploying 30 ground magnetometers, 30 of these RX888 receivers, and 10 whisper-son transmitters. So the network will now become an active network. And this also means that we'll be able to come up with our own modulations and transmit them and put together science campaigns. And this, I think, is where perhaps GNU Radio could come in, because in the sustain portion, there was talk of how do we build more partnerships. You know, there was discussion of how do we do small grants and small projects, you know, the kind of thing that might be the size of a senior project or a master's thesis is the sort of thing you could drive with GNU Radio. And so that's, you know, I think an area that would be worth exploring further, especially for both the purposes of things that occur as campaigns and experiments, but then also extending the analysis pipeline. So I know that there's work in integrating Whisper Daemon and KA9Q radio. Please continue to do that. I'm not well versed in that part of it yet, but I think that it's a wonderful thing that all of these different environments can come together. So with that, I'll acknowledge the NSF for these things. Thank you very much to GNU Radio and to the SETI Institute for making it possible for me to come here and speak to you today. I'll ask that everybody save the date for HamSci 2025, which is going to be at the New Jersey Institute of Technology, March 14th through 15th. We hope to see you there. It should be a wonderful time. For those who are curious about the personal space weather station, or at least the GRAPE part of it, this is a summary of the publications describing it, so happy to share this for anybody who is curious to hear more. And I'll leave it on this slide for how to get involved with HamSci. And I hope that if you are considering getting your ham radio license, that this has perhaps given you a little more reason to do so. So thank you very much, and 7-3.
Okay, are there, we have very little time, but are there any questions in the hall? Yes. And while I run over there, Kyle asked, where do I get a grape from?
Pardon?
Where does one get a grape from?
Oh, yes. Okay, so you can go to the HamSci website. If you go to hamsci.org/grape, right? And it'll take you to a paper that we wrote. There's this fantastic journal called Hardware X, and I'll mention for the folks in the room, there's also one called Software X, where you can put together documentation of your hardware, and it's like a slightly more rigorous version of like an instructables page almost, right? And that is maybe the most useful paper I have ever published, because if anybody has questions about the grape, I can just point them to that. So of those 100 stations, many of those people have completely built it on their own recognizance. If you choose to build one, the Bodnar is like $100, I think, to get the mini Bodnar that we use. That's the GPS disciplined oscillator. The board itself is available from Osh Park. And then it's a very simple soldering project. It's about, student level. The only tricky part is that the mixer chip is becoming unobtainium, so you might have to contact somebody in HamSci and they'll mail you one. But yeah, you can put one together, and I think it's a great introductory project, and it's been very good for high school level, things like that. Yeah.
Hi, thank you. A great presentation. I just want to know what your opinion is on the 27 megahertz band. Is there still a need for it, and can it be improved?
Okay, I caught megahertz band, and I think, was that 27?
27 megahertz citizen band.
Oh, CB?
Yeah. Citizen band radio, 27 megahertz.
Oh, yeah. 11 meters. Yeah, I don't think we've got any active collection on there. You can, of course, listen to anything you want. But I don't know what the rules are for that, as far as whether we'd be, able to do campaigns or things, or to quantify contacts. But, it's certainly there if there's interest. And I would recommend, if that's something that you're very interested in pursuing, shooting an email to the HamSci email list, because usually somebody comes out of the woodwork for a question like that one.
Well,
Thank you.
Thank you. Let's thank the speaker again.
All right.
Thank you so much. That was incredible, and a small token of our appreciation for being able to join this conference. We appreciate it.
So up next we have a talk on the Spallation's neutron source RF system, held by John Moss. Thank you.
Is it working? Perfect. Well, good morning, everyone. First, I'd like to thank the conference organizers for inviting me. At SNS, we love to get up and talk about what we believe to be a very unique application of RF, and that is the acceleration of charged particles. Okay, so why do accelerators need high-power RF in the first place? So we're gonna actually, this talk will answer this two-part question, right? Why do we use high-power RF, and how does SNS use it? So to start, we're gonna talk a little bit about some accelerator basics. I understand this is the last day of the conference. I understand there might have been a lot of fun last night that involved karaoke, so I'll promise you it will be very light. Only 2 formulas, 0 math. Then when we get through that, and you kind of have a little bit of an accelerator physics background, we'll talk about exactly how SNS puts RF to use. We'll talk about our ion source. We actually use 27 megahertz. The gentleman asked about the use for 27 megahertz. We can use that to actually make plasma. We will then talk about the cavity types. So at SNS, you can imagine we have a multitude of cavity types. We're really going to focus only on the accelerating cavities. We do have other RF cavities, I should say, that actually bunch the beam. And we'll touch on those, but I won't spend a lot of time on them. Then we'll talk about our high power RF sources. We are heavily tube-based, so if there's anyone in the room that still uses, triodes, tetrodes, knows what a klystron is, you're in the right place. That's what we're going to talk about. I just saw a hand. It was much, much less than 50%, I have to say. Then we'll talk about how we control those. We do have a nice little control loop, FPGA-based control loop that we'll talk about. Finally, we'll talk about the ring, a little bit more about beam physics, the ring specifically, how we accumulate our protons, and how we use those protons to ultimately make neutrons for material science. Okay, so everyone in the room, I think, understands there are 2 ways to accelerate, or 2 types rather, of electric fields, of E fields. We have electrostatic, and we have time varying. So let's talk about electrostatic for just a second, and why it is we do not use a DC field to accelerate charged particle beams really anymore. So what you see here is a picture of the Holofield facility at Oak Ridge National Lab. In its day, it was the world's leading electrostatic accelerator. It's advertised as a 25 megavolt accelerator. I think it actually went north of 30 megavolts. And I think it set a world record at around 32 megavolts. It's a tandem accelerator, so what that means is ions start at the bottom. They are accelerated to the top. At the top, they do some charge exchange, turn them from negative to positive, and then accelerate them the other way. That way they can get the most energy into the beam using the DC. So why is it, how do these things work? And why is it we don't use them really anymore? So you could think of it really, as you can imagine, it's like stacking batteries, right? You have these high voltage modules, you reference them to each other, you have to stack them up to come up with these really high potentials. And eventually it gets very difficult to keep standing that voltage off, right? You get arcs, you get breakdown. And the practical limit is about 30 megavolts. So you can see that Holyfield is about as good as it got when it came to DC acceleration. And to give everyone a little point of context, so at SNS, the hydrogen ion that we accelerate, we actually get that, we get it, its final energy level rather, is 1.3 giga electron volts. So to do that with DC, you would need 10 to the 9 volts. I mean, you can imagine that's really practically impossible to do. So we use time varying or RF fields. So here's a picture. I'll get into the details of this in a few slides. What you see here is actually a picture of our drift tube LINAC. And so the way that RF field works, so we take advantage of resonance, right? We use the resonance of the cavity to ring up a really high voltage in a gap. And it's tough to tell from that picture, but what you see there are tubes, drift tubes, and in between each drift tube is a small gap. We're talking literally centimeters, and we can set up a very high electric field, and when the particles pass through that field, they gain energy. As you can imagine, you can string a lot of these together in a really small amount of space and really get a lot of energy into a beam, and that's why, that's why we use RF instead of DC for particle acceleration. All right, here's the first of two formulas, the Lorentz force equation. I'm sure many of you are already familiar with it. I'll be very brief. It's basically describes the force a charged particle feels from an electromagnetic field, right? So we're going to talk a lot about the large capital E there, the E field. I'll spend a little time on the B field right now. The B field we use in an accelerator to combat space charge. So we focus the beam with it, steer the beam with it. The E field obviously is what we use to accelerate or bunch the beam. So I mentioned resonant cavities in the previous slide. So resonant cavities, you can imagine, also make a pretty good filter, right? We designed them to oscillate really at a very narrow band, more or less a single frequency. And the timing, the arrival of those charged particles in that resonant cavity is very, very crucial, as you might imagine. So the graphic down there that you see on the bottom of the page basically describes that. So what we want to do is we want those particles to arrive at the sort of, if you think of the RF as a sine wave, right? You want to think that the particles, if we want to accelerate them, want to arrive on the wave, on the rising wave, so that they get pushed. If they come in the wrong phase, they get decelerated. We have what we call beam loss, which means the beam scatters everywhere. You release radiation, bad things happen, and we don't get to do the fun science on the far end of the accelerator. So it's very important. The timing is actually a very important part of this whole equation as well. So RF cavity basics. Again, everyone in the room, I think, understands resonant frequency. So with a cavity, it's no different, right? It's just a big metal can. You shape that can, you change the volume of that can, and you can affect things like the inductance of the can, you can affect the capacitance of the can, and what you get is a resonant cavity. And so it's really easy to model. We just use a simple RLC model to start. You have a resistance, which basically is heat loss, right? You're bombarding this can with RF, you're going to get current in there, you're going to get heat loss. That's the resistance. The walls also count as the inductor, right? Or can be modeled rather as the inductor. And then the gap that I talked about, we model that as a capacitor. And the gap is probably the most important part, right? Because that's where we're going to put energy into the beam. And so I get this question a lot. How do you determine how much RF power a cavity needs? Well, really it's simple. It's two things. How much you're going to dissipate in the cavity. Most importantly, how much does the beam need? How much energy do you want to add to that beam in that particular gap? That's how we determine how much RF power we need. And you'll see here in a few slides, at SNS we're talking about kilowatts and megawatts of RF power. So here is sort of a schematic overview of the SNS, and I'm going to briefly go through the different RF systems that we have here on this slide, but we use a variety of RF cavities. And you can see energy levels here, beam energy levels on this graph, and we'll come back to these throughout the talk. But we have on the far left-hand side the normal conducting, so it's just room temperature. And then where everything turns blue, that's actually cryogenic temperatures. And those are superconducting cavities. And you can see right away, we get a large energy gain from about 190 MeV to 1.3 giga electron volts there at the very end of those superconducting cavities. So most of our energy gain is there. But just briefly, I'll go through all the RF systems. So on the front end, where we make our ions, where we start our beam acceleration, we have 8 RF systems. Those include some solid state amplifiers that you see there on the right, and then we have a tetrode-based amplifier that we use to actually ignite the ion source. This is an RFQ. I'll talk about this in a minute, but the RFQ stands for radio frequency quadrupole. From the RFQ, then we go into our MEBIT cavities. MEBIT stands for medium energy beam transport. So the MEBIT cavities actually do not accelerate the beam. They actually just clean it up. And they make these bunches that we'll talk about sort of at the end of the presentation. They make the bunches very clean, and that's important when we go to accumulate in the ring at the very end of the accelerator. So then once we exit the MEBIT, we enter into the true acceleration starts. Now, drift tube LINAC that I just mentioned a few minutes ago, and then our couple cavity LINAC, and I'll give you some more details on those here in a couple of slides. And then finally, the bulk of our RF systems reside again in our superconducting LINAC, and that is also where we get the majority of our energy gain. And I would be remiss if I did not mention the ring. Again, we'll come back to it, but here there's also no acceleration. The ring consists of 4 tetrode-based RF cavities, and they actually simply clean up the bunches and combat space charge as we accumulate more and more protons in that ring you see there on the far right. So I guess the main point that I want to make here is that we string together literally hundreds of these cavities using 131 RF systems to power them, and we pulse these cavities 5.2 million times per day, 60 times a second, 24/7, to make the 1.3 GeV beam. Okay, so first we have to have an ion to accelerate. We heard a lot about the ionosphere and bouncing radio waves off of it. Now we're going to talk about how we use RF to make an ion. So what you see here is a schematic view of our ion source. And the way it works is, first, I kind of lied. I said we use 27 megahertz. We are starting to use 27 megahertz. On the actual production machine, we still use 13.5 megahertz, 600 watts CW to ignite our plasma. So we have a low intensity plasma. We then pulse that with 2 megahertz at 80 kilowatts to really get things going. And I should mention too, and I failed to, that this is actually hydrogen gas that we're turning into a plasma. And what happens is, and I don't have a laser pointer and I apologize, on the far right-hand side of that schematic, well, I should say this. We actually bias this whole thing at negative 65 kV, okay? So what happens is, as these hydrogen ions interact with a cesium collar that I think you might be able to see, I can't quite read my own graphic here, but we have a cesium collar that the hydrogen interacts with. We heat that collar up. Cesium gives off electrons to the hydrogen very easily. It becomes a negatively charged ion, and then the 65 kV quite literally pushes the ions out into the accelerator. And so why do we use H-? I get that question a lot. That's a very good question. I'll explain more at the very end. It becomes, again, important when we go to accumulate protons in the ring. If you want to think ahead a little bit, think opposite charges attract. Okay, I went backwards, sorry. Oh no, I didn't go backwards. I think my slides are a bit out of order. So we have 4 main types of accelerating structures that I want to talk about specifically. So we already mentioned the RFQ. We're going to talk in more detail about our drift tube LINAC, our CCLs, and then our SCLs. So these are really these are the cavities that actually add energy to the beam. Starting with the RFQ. So we use the RFQ as a beam injector, and we love to use the word injection in accelerators. And so many years ago, before the development of the RFQ, which happened in, actually it's pretty old technology itself, it started in the 1960s. But prior to that, and until it really became commonplace, we still use large electrostatic accelerators to get the energy of the ions up high enough to actually get them into the accelerator. You can imagine if you don't have them going fast enough, they're not going to go very far. You can't get them in very far. You can't accelerate them. So the RFQ does that for us now. And actually it's unique. It has really 2 functions. Well, 3 functions, actually. It uses electric field to accelerate the beam. It uses electric field to focus the beam, hence the radio frequency quadrupole, right? Quadrupole magnet focuses the beam, and then it also bunches the beam. We talked about this bunch structure and how very important it is. So the bunching actually starts here in the RFQ, and we do that by using 4 vanes. You get an idea of what that looks like in that center picture there. And these 4 vanes are modulated. I'm not sure you can tell, but if you look at the far right, that's a vane from a recent RFQ that we purchased from a company, RI, in Germany. And you can see how that modulation increases as you go along longitudinally. And that increases because the beam is picking up speed. So at SNS, our RFQ operates at 402.5 megahertz. And our beam energy enters in at 65 keV, like I said, right, from the ion source, and it exits at 2.5 MeV. So it's pretty good energy gain right away. and 2.5 MeV is enough energy to get it into the DTL. So the drift tube LUNAC, or the DTL, they're really nothing more than a series of tanks. Inside these tanks, we quite literally have tubes. And what those tubes do is actually shield the charged particle from the incorrect phase of the RF. And so they're not just dumb tubes, they actually do have magnets in them in some cases, either electromagnets or permanent magnets, and we use that to, again, these are pretty long tubes, or pretty long tanks, excuse me, and the beam starts to diverge and get off track, and so we use those to help keep the particles where they're supposed to go. And so that's exactly what I just said right there. And so these tanks are driven such that you have the same field at all the gaps. Remember, we talked about the gaps very early on in the presentation. That's where the ions are actually picking up their energy. And so here's a nice little animation that's like 20 years old, showing you that this particle is happy. He's shielded from the incorrect phase of the RF, and then when he's in the gap, he gets to the correct phase and picks up speed as he goes along. So just like the RFQ, our SNS DTLs operate at 402.5 megahertz. Beam energy is 2.5 MeV at the entrance and 87 MeV at the exit. So now we talk about the CCL. So this is our last normal conducting type of RF cavity. And it's unique in that we have actually we have three types of cavities here. We have the accelerating cavity, then we have the coupling cavity, and we have the bridge cavity. So the incident RF wave actually enters the bridge cavity, and then it's coupled to each accelerating cell using the coupling cavities. I like to think of them just as sort of fancy waveguide, right? The RF just kind of passes through, doesn't stick around, and it only resonates actually in the accelerating cavity. So this is kind of what that looks like. What you see at the bottom left is sort of an ancient CST movie showing the electric field, and you get an idea of the beam comes in from the left there, and the accelerating field is the positive, and so it's only in the cavity when the RF cycle is positive. So as it passes through that first cavity on the left there and makes it to the second, of course the phase would be correct there, and so on. So here we've actually increased frequency. Mainly that's because the beam has picked up enough energy now, it's moving pretty fast. So now we've doubled our frequency to 805 megahertz. We'll be 805 megahertz the rest of the way. We enter at 87 MeV, and then we exit at 186 MeV. Now we get to the point where we're really going to gain some energy, our superconducting LINAC. So we operate our SCL at 2.1 K, which is about, negative, let's just call it negative 460 F. It's really cold. We use liquid helium. It's absolutely fascinating. I suggest if you're ever interested and you have another GNU conference, you should invite my counterpart. He'll tell you all about the physics of superfluids. Anyway, it's pretty fascinating stuff. So these are driven a lot like the DTLs, but they're driven in such a way so that every cell, so we have a 6-cell cavity that we use at SNS, and each cell, the RF phase is 180 degrees out. And the particles are only in the cavities when the phase is in the correct direction, right? So it's in one cavity, the field is oriented correctly. In the subsequent cavity, it's 180 out. In the next RF cycle, is you get the idea, right? So that's how the SEL cavities work. Again, we operate here at 805 megahertz, and we enter at 186, and then we come out at the very end at 1.3 giga electron volts. I should also say, I did mention this earlier, that at 1.3 giga electron volts, our hydrogen ion is moving at about 90% of the speed of light. So it's moving pretty fast. So we talked a little bit now, or previously, about the cavities. Well, how is it we actually get the power? So we have what we call high power RF transmitters, all right, and we generate megawatts of RF. Our gain from what you see, the low-level RF signal there on the left to the cavity on the right is about 90 dB, and that's multi-stage, as you can imagine. The first stage, we have a very simple solid-state amplifier. It takes that low-level RF signal in, amplifies it by about 30 dB. The output of that amplifier then feeds a klystron or a tube, mainly klystrons, and we'll talk about those here in a couple slides. They're the workhorses, right? They really give us a lot of gain, 60 dB, and they're the ones that we have output in the kilowatts up to the megawatt level. So just like the accelerator, we can divide our high power systems up, all right? We have 3 main systems. The one for the RFQ and DTL is effectively the same. And those are, you can see the klystron associated with those. That's the big silver klystron you see there. Those are 402.5 megahertz, like I mentioned, and 2.5 megawatt peak power. And I should also mention that we pulse the system. I mentioned that earlier. Our pulses are 1.5 milliseconds wide. So it's a pretty wide pulse, almost CW, almost considered CW anyway. It's 60 hertz. Then we have 805 megahertz, 5 megawatt klystrons in the CCL. You can imagine the normal conducting takes a lot of power to get energy into the beam. SCL, not so much, right? Superconducting is a lot more efficient. So there we only need 500 to 700 kilowatts, or 550, excuse me, to 700 kilowatts of peak output power to get the energy we need at that point in the accelerator. And those are the little bitty, as we call them, the little bitty red klystrons there on the right-hand side. All right, so a little bit about klystrons for those of you who don't know. So they're a tube amplifier. I guess that's no shock. They, of course, use a stream of electrons. We modulate that stream of electrons using RF cavities. The way it works is we pulse the cathode. So the cathode is a good electron emitter. We heat the cathode up. We then pulse it with a large negative DC voltage. That creates that beam. And the very first cavity, and you can see there's a picture there of a klystron halved and laid on its side, right? So the first cavity, we tickle in a little bitty RF signals. It's usually on resonance. And then that starts bunching the beam. And as those beam bunches pass the subsequent cavities, they actually introduce, or couple rather, a wall current, right, that mirrors the actual pulses as they go by. That wall current then sets up a voltage across the gap. We talked about gaps earlier. That acts on the subsequent electrons and makes the bunching even more intense. So ultimately what you end up with is almost an impulse. And you can tell, if you can follow that electron diagram there at the bottom of the little movie, you can tell that at the very end, the voltages in those cavities are so high, they're actually turning the electrons around and stopping them. So you have an electron beam traveling at about 60% of the speed of light or better, and suddenly you put the brakes on, you're going to get a lot of energy out of that beam. And that is how we use it to make high power RF. So now a little bit about the system that controls it. So I've already mentioned low-level RF. So low-level RF is actually what we use to close the loop between the accelerating cavity and the high-power RF system. It's got pretty good regulation, 1% amplitude and 1% phase. Just very briefly, what you can see here is actual operator screen. So this is what the operators use to control the cavities in the control room at SNS. And then, of course, the hardware. We use micro TCA, for those of you in the room who are familiar, and FPGAs to control this. I would be hard-pressed to tell you the exact model of FPGA, but just note that that's how it's actually operated. So the low-level system, the way it works is it compares the amplitude and phase of the cavity to a reference signal. It then calculates an error, right, and it corrects for that error. And the way it works is, so we sample it first at the fundamental, either 402 or 805. We down-convert that to 50 megahertz. Then the 50 megahertz signal is corrected, right? The amplitude's changed, the phase is shifted, and then it starts amplifying it. So the output of what we call the field control module then gets up-converted back to the fundamental. The fundamental is amplified using that 90 dB amplifier we just talked about, and ultimately provides power to the cavity. And there is your control loop for the cavities. Also, it does provide some protection functions, just as an aside there. So let's talk a little bit about the ring, and then we'll come to the end of the talk. So I mentioned earlier we have 4 tetro-based RF stations there in the ring. We have 2 that operate our ring fundamental frequency of 1 megahertz, and then we have 2 that operate at 2 megahertz. And their primary purpose, as we're accumulating these protons, is to keep that proton bunch tight, and then the 2 megahertz actually beats it down. So as they want to spread apart, longitudinally and transversely, the ring RF works against that to keep them tightly bunched. So now we're coming to the end. We've made it all the way through our accelerator. We're bopping along at 90% of the speed of light, and we're going to start accumulating protons. So how does that work? So I mentioned earlier, we actually accelerate a hydrogen ion. The ions are then injected, there's that word injection again, into the ring, where they strike a diamond foil. And that diamond foil quite literally strips the excess electrons off of the hydrogen ion, and it becomes a proton. You can tell here we actually have 3 beams that come out of injection. We have H minus, sometimes we just miss. We have H naught, where we basically it's a regular, for lack of a better word, hydrogen atom, and then we have the actual proton that we start accumulating around the ring. We dump these other 2 beams. Just as an aside, we are looking at other uses. They are actually relatively high power, not megawatt level power like the proton beam, but kilowatt level power that we could use for other science. So we start accumulating these protons with a multi-term process. I mentioned the ring RF. So basically what happens is these pulses enter, and it takes the period of 1 megahertz to make it around the ring. And this is one of the reasons why we use H0. So you can imagine you start accumulating a bunch of protons, you start getting these space charge effects. If we stripped the electron any earlier, we would have a lot of trouble getting more particles into the ring. So keeping it H0 actually helps combat that, since the light charges attract each other. And the other reason we use hydrogen is obviously it's a great source of protons, right? It's a single proton. It's very easy to get a proton from a hydrogen atom. So I didn't mention this very early on in the talk, but let's talk just briefly about the actual pulse, the 1 millisecond, 1.5 millisecond wide RF pulse, and what's contained in that. So in actuality, our 1 millisecond wide, so we have a 1.5 millisecond wide RF pulse, and in that we have a 1 millisecond beam pulse. That 1 millisecond beam pulse actually consists of a bunch of mini pulses that you see here. And this is the gap I was talking about. This is what the RFQ starts setting up, then the MEBIT cleans up, and so we get this nice pulse train coming down the LINAC. And it's long enough that if you grab the first pulse and you started walking, you would be to Nashville by the time the last pulse came out of the ion source. So it's literally that long. So what you can see here on the time structure, each pulse period is 945 nanoseconds. That's the same, that's the period of 1 megahertz, right? So quite literally what happens is a single pulse at a time goes around the ring. And you get an idea graphically of that accumulation there in the bottom right. And ultimately what we do is we compress it all the way down to about 700 nanoseconds, and that's what actually hits the target. And inside that compressed pulse is about 10 to the 14 protons. Right now the figure is 1.6, 10 to the 14. Ultimately, when we're finished upgrading the SNS, it'll be more like 2.3, 10 to the 14, so a lot of protons. In terms of current, we have measured up to 75, depending on the shape of the pulse, we have measured up to 75 amps peak. So it's actually quite a lot of current moving, at 90% of the speed of light. So a lot of kinetic energy there. So what do we do with it? So we take that that proton pulse, and we strike a liquid mercury target. It's liquid because things get hot, and it's easier to cool liquid mercury than really anything else. And so on an atomic level, this is more or less what happens. The proton strikes the mercury atom, makes it unstable, and then that mercury atom gives off 5 neutrons and 1 proton. So it remains mercury. And basically, scientists, and I don't have much to do with this end of it, so apologies for being a bit ignorant of exactly what happens on the far end. But basically, SNS is a material science facility, and the accelerator and the RF is more or less a utility. And this is really the end goal right here. We have material science from scientists from all over the world using neutrons to probe matter. So this is the end. RF-based acceleration is really the most efficient way to add energy to a charged particle beam. SNS, we have 131 RF systems that do that. They pulse 5.2 million times a day. And I'll just say thank you for the invitation, and I'm happy to take any questions you might have.
So, are there any questions?
Do you have to have your own power station to run this thing?
No, that's a good question. We do have, we do not have our own power station. We do have our own switch yard. ORNL in general, actually, I don't know if you went on the tour, but there's the Bull Run steam plant. If you are coming in via Solway, which is the way you would come from Knoxville, you'll notice a coal-fired power plant up to the right. That's basically there to support ORNL and I believe the Y-12 National Security Complex right next door. So short answer is kind of.
There's another question.
Great presentation. I was just curious what kind of sensing you have to have in the loop just to sort of know that things are going as expected.
So your question is about sensing, is that what you said?
Right, since it's a closed system in operation,
Sure.
I assume.
Sure, so we actually have, so specifically for our RF, we have, basically we measure power, right? We look for arcs, arc detection, just light, right? We have fiber optics that look at certain points, especially the high power side. We look for arcs, we monitor vacuum. Obviously we have to have the entire accelerator under vacuum. As far as the beam goes and making sure it's on track, we have beam position monitors. We have radiation detectors, and so these beam position monitors actually they give you a sort of a two-dimensional view of the beam spread, so you can look at it and you can tell basically is it is it the spread that you're looking for? And then the radiation, like if we have beam that strikes a place it doesn't need, it's not supposed to strike, right? It'll give off radiation. And whenever that happens, it will shut off the accelerator momentarily, but it does stop it.
Okay, are there any other questions? Sadly, that's not the case, so let's thank the speaker again. Thanks. So we have a short coffee break or morning break now. Please don't forget to buy your t-shirts and see you after the break. About a half, I think. Uh, One, two. One, two. Okay.
says 30. That, I don't think that's it. Anybody over? Oh, there we go. It is up there. Okay. So. Yeah, but if I can just, you know. Yeah, but it's like, but if I can just check from here, if I can read from here and I pull it there, more or less. Oh, that works too. Yeah, they might prefer that. Yeah. I don't want to be the difficult guy. Yeah. All right, everyone, let's finish up with the break and start our talk. And give your attention for Internet of Things technologies. The speaker will be Dennis. I forget your last name already, but please proceed and tell us what you know. Thank you. All right. Can you hear me? No?
I did. Okay. All right. Good. Good morning, everyone. I'm Dennis Joosens. I'm a PhD researcher at ID Lab, which is a research group at the University of Antwerp in Belgium, far away from here. And we also are affiliated with IMEC. You might have known from their chips. And today I want to talk about an implementation I did of a multi-channel -7 receiver, transmitter and receiver, to do some packet investigation and validation with GNU radio, of course. And that's not the right clipper. Is it 1 or 2? 2. Okay. And that's too far. So, Internet of Things, you might have heard from that as well. Typically, what they want to do is, have some low power devices which go long ranges, and of course, operate in a narrow band for most of the time, sensor communication. Most of the known technologies you might have heard of are like LoRa, which there were some talks this week about as well. NB-IoT and Sigfox, those are like, more or less the big players, let's say, in the field. And then we have -7. And it's maybe a little bit of an underdog protocol, but it's doing its, well, in terms of competing with the others, it can, get in line as well. So if I want to, why we are using it basically in our research group, I think we have been using it like over more than 10 years as well. And what I've seen as of use cases is for like localization. We had a few doctorates on that. Crowd size estimation even. For energy harvesting, which is from another doctorate, which was quite recently. Smart metering, of course, and in smart cities as well. I was actually also quite amazed that the standard itself is already 20 years old. As Arnold Schwarzenegger would say, old but not obsolete. So back in 2004, it got ISO ratified. And it originates actually from the ISO IEC 18000-7 spec, hence the name -7. Back then, it describes actually it described the parameters for active air interface communication at 433 megahertz bands back then of RFID. And it was originally actually created for military purposes. That changed a bit back in 2009, where the Department of Defense awarded like, millions of dollars. A contract for -7 RFID devices, software, and services to 4 specific companies to make it actually a bit more commercial, to get it out there, to make it more open, let's say. Also in that same year, -7 Alliance was announced, which they try to improve and enhance the spec and keep control of it, basically. And they did. And they pointed more into the direction of IoT functionality. As we see to the spec today, we see that it supports all sub-gigahertz bands. It is an open standard for ultra-low power mid-range sensor and actuator communication. And the version 1.2 spec is published in 2019, sorry. And they're working on the version 1.3, I heard, and that should come out quite soon. In cases of, to give some ranging cases basically, we have seen some applications that can go up from 2 to 3 kilometers, but the general practical use is about 500 meters where it's used. As I said, it's a full stack. This is to give you an idea of all the layers that it's defined basically. What I want to focus on is really like the file layer, of course, the more tangible layer, let's say, for this implementation. As you also might see, I make here like there's a bit of a gap between the two top layers and the other 5 layers. That's where the ALP layer, application layer, protocol layer, can be used for other technologies as well. For example, for Bluetooth, because it's quite a generic implementation, actually. And then, of course, you have the -7 alliance specification of the stack, which is quite specific only for -7, of course. As I mentioned, the Alliance protocol is an open source communication standard for mid-range communication. So basically, it also fixes the gap between the short range and the long range technologies. So it fits quite neatly in that. Looking further into the spec, it's a quite simple binary GFSK modulation that it's using. Most of the time it's GFSK. It has also FSK, but yeah, for normal purposes, not really used. The unlicensed bands, of course, the 423, 868, and here in America, the 915 band, which is used. It also describes 3 channel classes, the low rate, normal, and high rate. Name is a little bit self-explanatory, of course. You can put more bits the higher you go. What I used for my implementation is more the low rate. You can go also normal and high rate if you want, but that's basically playing with a bit more bandwidth and some parameters you need to change, of course. Also for my application, I come from Europe, so I use the 868 megahertz band to play around with. It has like a span of 7 megahertz, so can do quite a lot in that. And it also, the spec itself, if you look into it, it supports 2 sync word classes, we call it. That depends on which type of frame you're using. Background frames use typically sync word class 0, whereas foreground frames use class 1. Also, the sync word itself, it specifies the coding scheme that is used. Currently, there are like 2 coding schemes, as you can see. The most used is the PN9, which is the most simple one. It's a pseudo-random sequence scrambler, basically, based on a 9-bit polynomial. So my sync word that I wanted to implement was quite easily picked. Of course, you can start in using more advanced coding schemes as well if you want to, but I did not look into that. So, of course, we need to send data. We need to define how our packet is actually looking like. The spec defines it like this, as most of the technologies. A preamble starts. It has a sync word and a packet payload. The preamble and the sync word, they are non-encoded. The packet payload itself, of course, is encoded with the PN9, or the PN9 with half a FEC. These fields are used for time synchronization, frame synchronization. The payload itself, it starts all with a 1 byte payload length. Of course, the data itself, and it adds a CRC 16 at the end of the packet. Okay, so we can start building on our transmitter. I put it into 5 steps, quite common steps actually, which I implemented. Again, our frame, as you see. I use this multiplexer in GNU Radio with some vector sources where I can literally define my fields very easily. I do my mapping, so from 0 to 1 to 1 minus 1, basically. Simple mapping for GFSK, of course. Of course, the most interesting thing here is that I have the coded packets where I use the Python module, which does the PN9 scrambling and the CRC 16. Going forward, so we see this as the output, 0s and 1 in our packet, mapped to 1 minus 1. We literally see very clearly our, excuse me. So this was the flow graph, our unmapped bits and our mapped bits. Continuing to creating our symbols, our literally waveform, of course. We use a Gaussian shape filter, basically. So we upsample our symbols, or bits, sorry, our map bits, and we do some pulse shaping with a Gaussian filter, which we can define. You can find it very easily online, how the definition goes. And the most interesting characteristic here is the beta, which is the bit to symbol time rate, which basically defines the shape of your pulse, which is, quite important. So here you see like the definition of it, how I did it in GNU Radio. You can play around with the parameters, of course, but I try to follow the standard, the specification as good as possible. And we get our pulse-shaped sequence. For the baseband modulation, I use another block, an IIR filter, and so we need to integrate our symbols. In discrete time, we have to do that, so we have to find a way. We do that with an IIR filter with specific taps. We convert that to our complex value, which we feed then back to our SDR eventually. So what we see as an output, we see our space and mark frequency nicely popping up, which is a good result already. You can use any type of SDR, of course, to do this. Of course, it needs to have a certain amount of bandwidth for that. In this case, I used channel 0 to transmit on, following the channel classes, of course, of -7. When we look at the spectrum, we also see nicely the effect of GFSK and just FSK usage according to bandwidth usage. Also from the top, you see literally more energy at the left side, less energy, more concentrated on the right. Then the receiver itself, basically the reverse operation that I did. 6 steps I define here. So the down conversion, the reception, demodulating, time synchronization, frame synchronization, and of course the payload decoding. SDR reception, I made a small mistake here. The transmitter, it can be a much more smaller sample rate, but of course because we use narrowband frequencies, frequency band. And of course, at the receiver side, I really want to check at the full spectrum, the 868 band, to know if there is at least a signal in that band. You can do that, of course, wireless or wired. Then the down conversion, simple multiplier that I use, which is tuned to the center frequency of channel 0 in my case. I low pass filter that a bit to reduce some noise. The demodulation itself, as I said, reverse operation. We try to extract the phase. We take the derivative. Instead of integrating, we derive. We filter a bit because that interpolating FIR filter, that way of deriving, implements extra peaks we don't want in our spectrum, so we filter that out. High frequency peaks. Then I cropped up the time, frame synchronization, and payload decoding in one other parts to make it more clear. The time synchronization I do with a symbol sync you might be familiar with. I use a Mueller and Mueller timing error detector. You can, of course, use early late as well, or some else, something that at least outputs one sample per symbol. And if you also look quite good there, I apply a filter bank, which is also my matched filter that I apply. After that, I correlate my stream with I try to find the preamble, of course, and the sync word again in my stream. I add a tag to that to just visualize it better, basically. After that, then the heavy load starts. I do the PN9 decoding again. I check the CRC again, if everything works fine or not. And I put something to the logs of the console, basically, of GNU Radio. And of course, hopefully, I get all my bits back. I did some experiments with this, be it in a wired setup. I used a very cheap board for that. You can also, with that board, you can also do LoRa or Sigfox, so it's quite, a wide usage, basically. I set up a -7 node, a transmitter, and a gateway to log effectively, to see if my packet is really received, if it's really correctly decoded. And I saved all those samples with my USRP to disk. I used some attenuators there. Here I used another payload. The payload can be up to 256 bytes. 65 bytes, sorry. The sample rate itself here is 7.68, again, to have the full band, of course. Yeah, and then saving to a certain format setup that I had on my bench. I even, this is then the output that I get. I use 3 channels, channel 0, channel 93, and channel 186, to have one, yeah, more at the left, at the right, and in the center, more or less. Should give the same result, of course, right? 30 packets, and I could all recover them, of course, because it's a very controlled setup, wired, not that much can go wrong. And to check that if everything went wrong, you could look at the time domain, of course, at the console logs, and I put them here in bold. What you nicely see here is that my packet is, yeah, more than the bytes I defined. That's, of course, caused by the complete stack, which also add extra minimum frames, let's say, minimum fields to that payload in order to be seen as a real -7 packet, of course. But if you look closely, of course, in bold, I can get my message, which is 00ABCD in hex, back again. The 2 last bytes are the CRC. So everything went right, the CRC went correctly, so my packet is completely correctly received. I even continued that further with some experiments, indoor and outdoor. I'm not going to share the results with you. Of course, it was a bit worse. In terms of results, you have line of sight, non-lines of sight, multipath effects going on. But it was a quite interesting test. So I conclude with that I build a system that completely works. I can investigate packets, and the idea is also to, in the future, implement more parts of other layers, of course, to even investigate further on how it works. Of course, implementing the 1/2 FEC is also an option I can add. If you want to search for the files, they are all online on GitLab. The dataset is also published on Zenodo. It's in the SIGMF format, so you can check it with IQ engine very easily. And if you want to know more about the -7, all the links are there. Contact, of course, if you want to contact me. So thank you for your attention. And if there are questions.
And thank you very much, Dennis. One question, is there anyone that is doing -7? If not, thank our speaker again, and our next speaker can start getting ready. The schedule may show a little gap, but we're compressing this to allow some more GSoC, Google Summer of Code, results before lunch. So, and the AV team, he's going to present with his own laptop, and yeah, that should work.
Yeah, I've got it up, so. And I'm going to use this microphone. Okay, sure. Okay, so I'm going to go a little bit there.
Is our video team receiving his laptop video? Yes. All right, I'll hand you this microphone. Michael, yeah.
Yeah, hello. Good morning. My name is Michael Aldritt, and I'm an analyst with Sydney Trains, and I'm completing a PhD at UTS. So this presentation is on GNU, using GNU Radio in a multipath environment. So we'll just move on. So just an index basically showing what we're going to be discussing during the presentation. So moving on to an overview. So communication links can be created by modulating data on ultrasound, allowing information to be exchanged between devices. And sound propagates really well in liquids and solids, where traditional radio systems are attenuated. So for environments that you can't use a radio and RF doesn't work very well, modulated audio is an alternative solution. So transducers are used to basically convert the electrical energy to sound energy rather than to RF. So one of the project objectives basically is to allow high rail vehicles, which is road rail vehicles, to communicate with each other on the wayside when they are traveling in groups using ultrasound. So the transducers can be mounted on the track, and you can have another transducer in the cab. So you can have a device in the cab and it can communicate with the track, or you can have a device in the cab and it can communicate with another road rail vehicle in front or behind it. The rail wheels that actually go on the track are the means that the link is actually formed between the vehicle and the actual track itself. So how is this achieved, and what are the issues that need to be resolved? So the project uses a sound card as an analog to digital and digital to analog converter. And this is an alternative way of actually using GNU radio if you're not using an SDR. The audio frequency used is at 40 kilohertz, so we need to sample at more than twice that value as per the Nyquist theorem. And the sound card uses a sampling rate of 192 kilohertz, which is more than 4 times the value. So this allows a modulated ultrasound signal to be transmitted in the transmit transducer and demodulated in the receive transducer. So the issues encountered when trying to propagate in a dense material, such as steel, is as follows. The signal can take a number of different paths through the material arriving at different times, and the received signal has too many errors to be demodulated properly and the link fails. So in a normal radio, you only have a transverse wave, but in sound and in solids, you can have both a transverse and a longitude wave, or both. So you're having these issues not just with multiple transverse waves, but also multiple longitude waves. So it just complicates things a little bit. So what is multipath and echo? So when you look at just a normal multipath in audio, so you're looking at basically like the audio is reflecting off a hard surface, or it might be the actual boundary of the actual material, or even in water, it might be like just areas where you have different densities, and that wave will actually bounce off and be reflected back. So as in the image there of the water, you can have like, you know, a direct transmission, or you can have it bouncing off the surface and coming back. So the receiver can get overwhelmed with all of these different pathways that the signal is arriving. So with wave interference, right, it can be caused by, it can either be constructive interference or destructive interference. So it can either reinforce the signal, or it can actually destroy the signal. So there's just something that you've got to actually be aware that, you know, it can be either a better signal or a worse signal, but with multipath, you won't get the right signal all the time. So what modulation techniques are available, and how well do they perform? So I've done some tests, and initially I was testing with binary frequency shift keying and flow graph and a sound card. And the FSK, the transmit and receive testing on a number of different substances. An image was modulated onto a data stream using ultrasonic transducers and transmitted through the substance. The baud rate that I was using was at 1200, and allowed the file to be sent in a reasonable time, which is about 5 to 10 minutes for a 70K file. The RX transducer picked up the received sound wave, which was demodulated in the software, and I got reasonably good results. So I was doing text and images and audio files through the actual substance, and I created a tank to basically hold the liquid if it was doing. So the tank used created a lot of reflected sound waves, and a cover was placed around the RX transducer to limit the interference I found that putting a shield over the transducer actually helped quite a bit. And some material failed, and are listed in the results slide a little bit further on. So this is kind of the setup that I was actually using, right? So I've got a sound card, and I've got an actual a tank. So I've basically put every sort of like substance I could think of into that tank. And on the in the image on the right-hand side, we have blue laundry detergent, which I thought I'll try and see how I go with transmitting through that. And I did actually, with the tank, I did put a corrosive substance in, gas, and it did actually kind of destroy the tank, which was unusual. But anyway, I got through that one. So just moving on, this is the actual binary flow graph that I was actually using. Barry helped me with the actual post and preamble on this, which made it work. So if you're trying to actually have two devices and actually communicate with two devices, the post and preamble allowed the actual signal to synchronize, the receiver to synchronize with the transmitter, and you actually then got really good results. So again, this is showing the post and preamble, and you can see the actual the preamble there, I think, is to begin with, and then the actual data flow. Next one. So these were some of the images that I was actually using to actually transmit from one computer to another, and so they were at 70 kilobits. On this, I'm only showing one computer, but I've done this with a number, with two different computers located separately, so it does work when you're actually using separate devices. If I didn't have the post and preamble, it wouldn't work using this method. So these are some of the results that I got from actually using binary FSK. And obviously in water, well, you're not going to use this method for transmitting in air because you just use a radio. But for the other substances like water and petrol and diesel and milk, it actually worked quite well. And even down to some materials that were not so dense, like pine, I was still able to transmit like the actual image through the desk, which was made from pine, and I thought that was quite good. However, the what I wanted to transmit through was steel rail and hard material, and that failed. So I had to sort of think of another way of actually doing this. So in normal RF transmission, so what other solution can I use? And is OFDM a solution when FSK fails in a dense material? And the other question was, do I have enough bandwidth, right? Because the ultrasonic transducers have a cutoff point of 41 kilohertz on the upper side, upper part of the spectrum, and 39 kilohertz on the lower part of the spectrum. So you're working within a very small bandwidth, and you really need to have, with OFDM, you need to have spectrum. You need to have, like a spectrum for it to work. And I only had a little bit of spectrum. So in normal RF transmission, OFDM has been a great benefit to resolve the issues with signal ghosting from multipath. Radio and TV reception has improved exponentially as a result, especially in locations where there are many structures that can block or reflect the signal. So some of us will remember, years ago, if we were picking up TV on the original, signal, and there was reflection, you'd get ghosting on the TV, and it could be very hard to watch anything because it was just the reception was so poor. So with OFDM, when that came along, right, and they went digital, a lot of these ghosting issues were resolved because of the brilliant way that OFDM works. The subcarriers used are very resilient and are not corrupted easily as opposed to the more traditional transmission protocols. And there are many applications using OFDM, like Wi-Fi, for example, uses OFDM, LTE, TV, DSL, ADSL, and VDSL. They use the same structure with discrete multitone, so it works on telephone twisted pairs, which is quite good. The OFDM structure reduces the impact that multipath and crosstalk have on the transmitted data. So, next one. So we've confirmed that FSK is a great solution until we get to dense substances such as steel, rock, aluminium, and heavy plastics. And we know that tones can be heard in metals like rail in long distance. So a lot of people say, well, if you listen to a rail, you can actually hear the train coming, and it might be a long way away. And the reason for that is because the speed of sound propagates through rail 20 times faster than it does through air. And so the range is actually significantly further. So you can hear sound traveling through dense materials, not only a lot further, but also the signal does propagate further as well, yeah. So ultrasound, using ultrasound, it's above what people can hear in the normal audio range, so there's less interference at that range. There's less noise on the 40 kilohertz spectrum, which is great because you don't have interference from other things that we would normally be listening to. So OFDM is normally used in a broadband solution. Again, that's looking for bandwidth in megahertz, and I've got kilohertz, which is not good. And again, getting back to the transducers, the normal range for a normal ultrasonic transducer is about 1 kilohertz above or below the actual the spectrum, the 40 kilohertz, and it's just a design thing within the actual transducer itself. So you can't take it apart. There's no filtering or anything like that. It's so the actual solution was to try and get transducers with a bigger range, and that's what I did. I wanted transducers that had maybe 4 or 5 or maybe 8 kilohertz, but I managed to get one that had 3 or 4, and that was just enough to actually run the flow graph without breaking it. So this is just a great representation of OFDM, and you can see the subcarriers and the symbols, and it just shows the mechanism of the actual the channels, which I think is a very good graphical image. So next one. So to do the test, I was basically using a Ubuntu laptop with GNU radio. I do have Radio Conda loaded on my laptop, but the audio, changing all the audio settings on my laptop was not something I wanted to do because it might not work after. So the USB sound card had a sampling rate of 192 kilohertz, so I set the sampling rate in pulse audio for 192 as well. The transducer had a bandwidth of 3 kilohertz center frequency, and at 40 kilohertz, and the serial track with attached transducers and audio plugs. The text test file to compare the output with the original, and I had an OFDM flow graph that was being used using a simulation config. And the flow graph I used, I found one that Quasam Chowdhury had actually modified before. I think he got it from somewhere else, and then I modified it again to actually work with my hardware. And this is the actual the graph. And one of the things that's quite nice, because when you're using a sound card doesn't take a complex signal. So Quasam found this really great way of actually taking a complex signal and actually then bringing it back to a normal signal that could actually be fed into the microphone as a float, or into the speaker as a float, and then actually output it as to a sync, to a source as a float, to be able to be demodulated. So this actually worked for that, but if I could have got a SDR that worked at 40 kilohertz and accepted a complex signal, it would have made life so much better. And again, this is the receive, and again, we're using this method of taking the virtual source in and then actually combining it to get a complex where it can be taken into the rest of the flow graph to be demodulated. So this is roughly what my setup looked like. Again, I was just using a Ubuntu laptop, sound card. These are very good sound cards, and I went through so many different sound cards to get ones that actually did what they said they were supposed to do, which sampled at 192 and not at something else. And I basically have my microphone and my speaker connection. It's got an amplifier in it, which helped a lot. The ultrasonic transducers, these were really good transducers that I found. They had about 3 or 4 kilohertz of bandwidth, and they just held on the track with some blue tack. And that seemed to work and seemed to do the trick quite well. And this is 0.5 meter of 60 kg rail, which is standard rail that's used in railways all around the world, including the US. Yeah. So this is what the flow graph looked like. So, you know, just some screenshots from it. And you can see I'm getting everything that I need to, the constellation and the actual stem graph. So I was really pleased with that. And now this is a short video of the actual test. So I'm just going to play it. It goes for about 2 minutes, so it's not too long. So just showing the actual, when I started up, this is the rail, right, that I was using. And you'll see in the next second or two, it will show where the constellation comes in, which was very exciting at the time. So just there, you can see the constellation has come in, and then we're actually getting data into the actual, into the target file. And again, you can actually see we're at 40 kilohertz. And we've actually got we've got 3 kilohertz. We've set the actual variable at 3 kilohertz for our bandwidth. So just as it comes on, and so it didn't take too long. Now the reason I used a text file rather than something better, it just meant I could have the text file on repeat, and it meant if there was any issues or whatever, it would be repeating. So if there was a problem, if I did have an error, and then the second time it repeated, I wouldn't get that error again. So after I ran it for a little bit, I came in and I opened up the actual the test file. So I was using the Gettysburg address, one that Barry supplied, and I actually, and again, this is the actual transducers, and then I'll just open up the text file. So when I tried this previously with BFSK, it just did not work. It would work in air, but it would not work when I actually put the transducers onto the track. And I think I'm going to open up the file, which is, so there you go. So this is actually the target file, and you can actually see it's there's about 4 paragraphs, and I put line breaks then in between where it was repeating, and you can see it's actually repeated a number of times. So that was very exciting, and I was really thrilled when I could actually see that I was getting proper data flowing through the track. And I believe that the range I can probably get on this could be 30 to 50 meters, because I've done that with just tones previously. So I know that it could actually work for a range of about 30 to 50 meters. So I think that's kind of the end of that one. So that shows up. So again, this is just showing the actual source file and the target file, and the source file was basically the same as the target file, so it was really and then so improvements that are planned. Okay, so the FSK flow graph had a pre and post amble, which I think will probably have to be added to this OFDM graph. I want to tweak the flow graph to see if I can reduce the bandwidth to lower, maybe 2 kilohertz if possible, without breaking it. And I also want to test it with images and audio files where when the flow graph is improved, and also testing with other dense materials like rock and other hard materials. I still have to do some testing on that, and basically tabulate the results from these improvements. And maybe the transducers, I don't have any shielding on the transducers, but that's something I want to actually put like a ground shielding on them, and finding a better transducers that have improved characteristics and performance. It was really hard to actually find a transducer that had any bandwidth. They were all, so I did find one that had a bigger range than 2 kilohertz, but they weren't easy to find. And yeah, so this kind of is where we're at, and I'd just like to thank everybody for their help and support. And I hope you've enjoyed the presentation, and if there's any questions or comments or anything like that, I'd be happy to answer them. Thank you.
Thank you very much, Michael Aldritt. Got one question on multipath.
I was surprised you didn't mention DRM among the standards you listed when you were talking about OFDM. Are you aware of DRM? Did you try anything of did you try it for?
No, I didn't. But like, what I had available at the time was I know OFDM will work because it's great for using in a noisy environment, and it's tried and tested like in normal RF. But I wasn't sure. Maybe after the break we can have a chat, and we can talk about maybe a possible other solution.
Very interesting. I don't get any money for this, but AirSpy plus HF discovery goes down to 0.5 kilohertz for an SDR if you wanted to use that. The other thing is transducers. I know the Navy uses very high frequency transducers like 2 megahertz or something.
Yeah.
I'm not sure if you tried any of those. And I guess the other comment, were any animals harmed during these experiments?
No. No, unfortunately. But look, transducers were a real challenge, trying to find transducers that had bandwidth. And yes, you're right, you can use it at a higher frequency, but I'm using a sound card, and the sound card basically had a 40 kilohertz. The maximum frequency I could go up to on the sound card was about 90 kilohertz, so I'd stay under the 192. I was trying to get a sound card that was actually had a higher sampling rate, but even the ones that were labeled, I got a couple from on eBay, and they said they were 384 kilohertz, and they weren't. When I looked at the chip, it said 96 kilohertz. So it's getting an actual sound card that has a higher sampling rate. That's what I found a problem with as well. So I couldn't go too much above 40 or 50 kilohertz. Okay, thank you. Clayton.
Yeah, I'm curious what your what OFDM parameters you use. So how many carriers, and what your symbol rate was, and whether you needed to make any adjustments to those to get good performance, or if things just kind of worked with the flow graph you started with.
Yeah, like managing with the FSK, I had a mark and a space. It was binary. That was easy enough to resolve. But with the OFDM, I'm still a novice in many respects. And I was using the blocks that had been already developed, rather than being able to fully analyze and understand how they were actually working. But I know I was able to get it down to 3 kilohertz without breaking it, so I thought that was good, you know. But yeah, so maybe there will be scope for improving that to either reduce the size of the carriers, the subcarriers, or to actually get transducers that have a bigger bandwidth.
Thank you very much, Michael. I know our GNU Radio OFDM team is delighted to hear that this was a success for you.
Absolutely. So if you don't have an SDR, you can use a sound card.
All right, let's thank our speaker again. And our next speaker, Matt, can you start setting up?
Thank you.
One, two.
All right, let's turn from multipath into machine learning. So here is Matt, and to tell you how he did it.
Thanks for having us, everybody. I'm Matt Carrick, and Area O is going to be talking about some of the work she's been doing later, but I'll get us started on TorchSig. So TorchSig is simply kind of the core idea is it is a system for RF machine learning. There's two main branches if you really break it down. There's the machine learning side, there's what the models are, there's how do you train them, those interactions, and then there's also the signal generation. So we'll talk about that more a little bit, but it's all the different data sets we can generate, the different formats, and then so TorchSig puts all those pieces together to make a machine learning system. So if you go to torchsig.com, if you go to torchsig.com, you can download the source code, you can download papers, we have pre-trained models. Some of that will be changing in the future, but it gets you a good start. And then that will link you to the GitHub. So if you're interested in running it, you can go today, right now, do a git clone, download all the source code. We've got a bunch of new examples and things there for you to run. So I said, we've got some machine learning models. We've got narrowband and wideband. So narrowband, you can think about this as if it's been channelized already. So it's at complex baseband, it's resampled, and it's as if it's been time-aligned. So it's been put through an energy detector, and then we've got a wideband model, which is it operates on spectrograms. So you can look at signals in time and frequency. So my favorite part, the data set generation. So we've got a couple different waveforms you can look at. We've got FSK, GFSK, all the QAMs, all the PSKs. So we go through, generate those for you, and then you can apply the machine learning to that. So we've got spectrograms, and you see a bunch of different waveforms on here. So at the top, we've got 8 FSK, 128 QAM, these kinds of things. So it generates a single signal for you. And then at the bottom, it will generate a bunch of overlapping signals, higher complexity for the machine learning to train against. All right, recent updates. So we have a couple updates on the website that you can download. It's making things faster, less memory, reducing size on disk, and we also added a bunch of DSP updates, new examples, those kinds of things that are a much better tutorial for using TorchSig for new users. And now Ari O will talk about the rest of her contribution for synthetic spectrum generation.
Hello, so I will be talking about two novel things that are new about TorchSig. First is the synthetic spectrograms, and second is a GNU radio block. So just starting out with spectrograms. Spectrograms are just a visual way of representing signals across a spectrum. And this is very important because now your signals are in the image domain, and you can use a lot of image-based machine learning techniques to train a model to detect these rather than in the IQ domain. You can imagine these models drawing a bounding box around these signals at the correct frequency and time. So I feel like everyone knows that. But getting more about synthetic spectrograms, currently TorchSig has the ability from IQ data, like SIG53 and wideband, to convert to spectrograms, but that's very computationally expensive. Creating just synthetic spectrograms straight up in the image domain is a lot faster, and it's a lot more quicker, and this results in being able to quickly create a data set for your machine learning models. And I'll talk about two main things about these synthetic spectrograms. One is augmentation. So if you have a signal, you can augment it. And two is just general creation of signals, which I'll go into in a little bit. But this solves a lot of the problems in terms of the data set problems you might have with IQ data. The first is basically being able to augment signals. So let's say you have a signal of interest and you want to train a model like pretty quickly to detect this. You can use few-shot learning, which is basically training a model on only a few examples to detect this particular signal. And you can do this by basically taking those few examples that you have of your signal of interest, train a model, and use our TorchSig tools to augment this signal. So it's not just cleanly throughout the spectrogram. It has noise, it has frequency hopping. You can see a little example there of recycling narrowband. And this is really valuable in case you want to quickly train a model to detect a particular specific signal and like augment your current signals that you already have. But going into like creating your own signals, like our typical modulation schemes, we can also do that from scratch, just simply in the image domain. So here's an example of creating like a chirp-based waveform, and that's like a lower-like waveform, and you can see this is all done in image domain. There's no IQ data behind this, but I'd say it looks pretty realistic. And going into like how that all works, we use context-free grammar, which is a mathematical concept of creating very complex patterns. And you can see more examples are in the code, but you can really up your complexity of these custom signals you can just create yourself without having to go out and collect it yourself. And you can see here, this is how you can just put it all together, these composite spectrograms with your own custom signals. And just to remind you, there is no IQ data involved in all this. This is all just pixels and images. So feel free to throw your image-based machine learning models at this and have it learn. And we've proved that training on synthetic spectrograms translates very well to the real world. Taking a little fork in the road to the GNU Radio, which is the conference we're at, we have now created a GNU Radio block for inserting your own machine learning model into your flow graph. So in this example, we've trained YOLO V8 on the ISM band. We've trained it on, to be clear, not synthetic spectrograms. That was just the previous feature. This is just on our dataset wideband 653 on those images. And we've trained it to detect signals, and this is an example of the flow graph, and this is an example of some of the parameters you can do on that GNU radio block. It's not fully featured, but obviously still in development, but you can parameterize a bunch of aspects of this model. And here's a quick screenshot, and we're gonna do a quick demo in like a couple of minutes to show like this in live time, but I'd say it does a pretty good job of quickly picking up signals and running that model in real time. And just to go over some future work, obviously we are always trying to improve our data sets, and especially allowing users to use TorchSig with their own custom data sets, especially integrating with Label Studio. And as always, like trying to add more integrations with machine learning models like Hugging Face and PyTorch, and improving our synthetic spectrograms. There's a lot of work that could be done in that space for creating even more realistic or complex synthetic spectrogram signals, and not all of the modulations we have currently implemented. And lastly, we have more modulations coming in the way, so the name SIG53 will have to be refactored because there's more than 53 signals, but these are exciting stuff that's coming up for TorchSig. We'll run the demo real quick. I'll just take this HDMI, but if you have any questions, you can think about it. So this is the flow graph that it's pretty much the same as given in the screenshot, YOLO trained on our wideband data set. And this is just it detecting signals in live time. I know it's a little fast, but this is just live right now on this laptop. So I can take questions while this runs.
All right, thank you very much. Where are the questions? We got one here, I got 3 of them, so.
Hello, I have a quick question. So when you talk about synthetic spectrograms, so there's no phase information anymore, like you're only using the magnitude?
Yeah, so as you know, like a lot of information is lost when you translate to spectrograms. So there's no phase information, and it's very hard to recover phase information from spectrograms. So yeah, no phase information.
And how did it compare with the full IQ based spectrograms? Did you guys do a comparison?
Yeah, we did a comparison, and it's just, they both work really well. You can just choose which data set, whether the IQ data set or the spectrogram data set, but the images just have this edge over, like, it's much faster, it's much quicker. If you need something quick and dirty, like, get it done. But obviously, if you want the full, like, specific in-depth, like, phase, with, like, phase included in your model, you should probably use the IQ data. So, hope that answers your question.
So I'm wondering about like unknown classes of modulation. Like, is your energy detection algorithm able to pick out an unknown class of modulation that you have not trained your model on?
Yeah, so going along that, I think we want to be able to. Is your question like how does it do on modulations we haven't seen before. Is that your question? Okay, gotcha. Essentially, by adding these augmentations and these synthetic spectrograms, we're hoping that you can train models that are more robustly or adaptable to these like unknown signals, and that you can't just like generate, that's quicker to generate than IQ data. But obviously you can pick these signals up yourself. But that is like the general idea, is that being able to create these synthetic spectrograms, you can quickly have a more generalizable model, or you can make your model very specific and fine tune it. So that was the idea.
Hi, I'm with them. But just to clarify, it does generalize sometimes. We're working on different ways of helping to improve generalization of the models to it'll pick up unknowns. It doesn't always do a very good job. It's very important to fine tune on the specific type of models in a specific spectrum. It'll perform very differently. This is trained specifically on the ISM band. If you try to run an HF spectrum through here, it's gonna crap, right? So you gotta fine tune on that particular spectrum band. Also, the data sets are very dynamic. You can, it comes out as complex IQ, and we have a bunch of transforms. So you can generate spectrograms based off the IQ. You can break it up in its real imaginary components. You can do whatever you want to the data at that point. You can write your own transforms and put them in there to do whatever you want with the data. But there's two different types of spectrograms. There's the spectrograms based off the IQ, and then there's the purely synthetic image domain spectrogram. So just to clarify. Not at the moment, no.
All right, is there another question? Yes, we have one.
What's the minimum hardware that you need to run TorchSig?
I don't believe it's very much. I think Matt has a better idea.
I would say a monitor, it depends on how long you want it to take to train, how long it to take to generate data. A modern laptop, so we're running just a, reasonable laptop with a B210. If you wanted, I would suggest a GPU with it. That's probably the minimum, but it's nothing beyond that.
And I have a question which I think I already know the answer. So since PyTorch is so popular, your GNU radio block would be a Python block?
I didn't code it. I think it's a C++ block.
Oh, there we go. Because it's being very performant in your demo. Thank you.
I was just wondering if it was able to correlate one of these synthetic images back to an IQ data, if you had a recording of it in your data set or something to analyze it later.
Yeah, so I think what you're saying is, can you extract out the IQ based on the spectrogram? So it'll spit out, I don't know that this block will interface and give you that information. If you want to dig into it, you should be able to pull out center frequency bandwidth and then do the channelization on your own.
Are there any more questions? Oh, we've got one over here.
Do you have the ability to manipulate the power levels so that you can make your signal appear in a high SNR or low SNR environment?
Yeah, so although I kind of skimmed over it, most of the stuff in TorchSig is able for you to tune your knobs, tune your parameters as much as you want, add your own data, add your own transforms. I hope that answers your question. Is that right? Okay, we can talk later.
All right, let us thank our speakers. And there will be lunch, a full lunch, just like any of the other days at noon. But the caterers would be terrible if I let any of you out. So please, we can learn about some of the student contributions to GNU Radio. And you can introduce yourself. Oh yeah, well, let's wait for the AV team to get his slides up. These are the GSoC. All right, we can use this laptop. All right, looks good. Andrej, tell us about Google Summer of Code.
All right, all right. So, I should use the mic. Oh, just leave it here. Perfect. Okay, as it says on the slides, my name is Andrej Rode. I'm here basically representing GNU Radio. I've been a GNU Radio contributor, and I've been also doing things in the organization, but I also had the pleasure to be a GSoC mentor this year for my second year. And since no other people from the current GSoC part of GNU Radio are present this time, I took the opportunity to tell you a little bit about just what GNU Radio is doing with Google Summer of Code, or Summer of Code in general. Yes, perfect. Thanks. So first, a little survey. So who knows what Google of Summer of Code is? So it's about half, like always. Thanks. Who participated in Google Summer of Code as a student or as a mentor? So that's not about half. That's basically just a few people around here. And who in here is an educator working with undergraduate students or graduate students? Okay, a few. That's cool. So you should stay. Don't leave, please. So what is Google Summer of Code? So Google Summer of Code is basically Google having a bunch of money and trying to support open source projects. How that works is basically projects can register or sign up with Google and then propose ideas and then basically get a summer intern which is paid by Google to participate in this open source project. And yeah, GNU Radio was quite lucky to be able to participate since about 2012. And there was another project basically copied by the European Space Agency, which was called Summer of Code in Space, which was only held a few years. But also GNU Radio was part of that. So to give you a brief timeline about all of the projects and all of the students that had the pleasure to work with GNU Radio and with GSoC, I just copied together a bunch of information so people who don't know what was accomplished in all of these projects can have you can get an idea. So it started with 2012, and then basically every year there were like at least 3 or 4 projects. You see 2014, there have been 5 projects even. And if you look at the names behind there, there's names that are also sitting in this room. Like there's a Markus Müller, there's a Johannes Demel, and on the other side we have other people that are also still around, not in this room, but like for example in 2017 Hakon participated as a student, and now he is basically the project administrator for GNU Radio. So he is basically running the whole GSoC part of GNU Radio, together with some other people. So in the last few years we had fewer and fewer projects. So sometimes, if I go to the slide before, so you see there is a gap in 2018, and also in the last 4 years, basically 2020, 21, you see there's only one project, and that's not because Google wouldn't give us more projects. It's mostly because we are lacking, let's say, participation by students and also educators and mentors submitting ideas. So this is sort of also meant as a, let's say, motivation for you to contribute your idea and mentor a student, or let's say send your students to GNU Radio to propose their participation. And yeah, not to forget, we have a long list of mentors, many of which are also sitting in this room. So we also have to thank them for spending their time mentoring students and advancing both education but also the current state of GNU Radio. So implementing new features, doing cool projects. And how is this currently organized? As I said, the main guy right now is Hakon, and he's organizing things on the project side, like talking to Google, doing all the admin stuff. He's also supported by Sebastian Kozlowski, who also was mentoring before, so like, yeah, there's a lot of overlap in mentoring and also running the project. And for the past 1 or 2 years, yeah, or I think for this year, those are the mentors that were active in mentoring. So yeah, I got the pleasure to mentor a student as well. And yeah, maybe for 2025, you can also be part of the GSoC organization. So basically, you just have to propose an idea or send a message to Hakon or Sebastian if you have an idea, or if you just want to mentor and you don't have an idea, you can also just sign up. And a few reasons why you should participate. So as a mentor, you can have a cool project. If you are, most of you here, you are basically running on a lack of time. So you have a lot of cool ideas, but your time is limited in your free time or even in your professional time. So you can basically just have a free student in the summer who gets paid and implements your idea. And the only thing you have to do is to help them. And as a student, of course, you get paid to contribute to open source, which is, let's say, if you get started with open source, it's not as easy. So, and you can do a summer internship at a new exciting community and get in touch with many people and also have your work publicly available. So that's also always quite nice, and you not always get the opportunity if you work at a company to get like public code. And of course, as an educator, you can excite your students and send them to the GNU Radio project, and they will be implementing a cool project in the summer term, in the summer break. And then in the next semester, they come back with many more ideas and many more experiences. And they might become very good DSP experts. So just to give a rough idea about a timeline, how it was this year. So basically, it starts in January, when GNU Radio will basically again register with Google, and we will try to be accepted as a mentor or as a project organization. And then basically around February, we will have to publish ideas. So this is also where you come in. So if you have an idea, you can already, later there will be a link and a QR code to a wiki page where you can just already put your idea in. But basically by the beginning of next year, you should have contacted us with your willingness to participate and also with a possible idea. So then more or less in May, the students that get accepted, they get in touch with the community, they send a few emails, they fix a few easy bugs and get started with coding. And basically by the end of May, the students are more or less half or full-time working on their project with their mentors until the end of August. And since a few years, GSoC has also adopted a model of different sizes of projects. So some of them can be, I think, as short as 6 to 8 weeks, up till 12 weeks, if I'm not mistaken. So yeah, students could also just spend a few weeks instead of 3 months. So yeah, this is the QR code that goes directly to the link below. So this is just on our wiki where we propose ideas and also propose the possible mentors. So if you have an idea and you want to mentor yourself, you can just add a new entry, and also please then contact us so we know about you and your idea. If you just have an idea and you don't have the time to mentor, still add your idea, and then of course you should talk to us, because then we might be able to find someone else within the GNU Radio organization or someone else who's contributing actively to GNU Radio to support and mentor your student, a possible student. Yeah, that's basically all I have to say. If you have more questions or comments, you can send me an email or a matrix message, or you can also just contact our GSoC project administrators directly via Matrix. Yeah, and I'm also happy to take any questions if you have any.
All right, well, let's give a round of applause to Andrej for his efforts. And I wish to thank you as well. Do we happen to have any good GSoC ideas that we can take from the audience right now? People are busy formulating. All right.
Like very obviously, we've got Radio 4.0 coming up with huge amounts of work to be done. And a lot of these works are, you know, finding applications which might not be the perfect thing for a student to do, but there's also very important work in porting, analyzing what is the wisest way to do something. So we can do a lot of things. And well, I'll be happy to mentor, and I get there's much more.
So may have missed this part, but say you have an idea and you reach out. I mean, we can get other people in the community to help potentially mentor.
Yes, correct. So if you just have an idea and you don't have time to mentor, like reach out to us, or add it in the wiki and reach out to us, and then we will be able to figure out to find someone else to mentor. I mean, yeah, even if we don't have the domain expert on like this particular topic, most of the mentors that are currently on this list, they can help coding and also figuring out bugs and other intricacies with working with other C++ projects.
All right, anybody else? Thank you, Andrej.
Thanks you.
And yeah. We're going to do closing before lunch, but I'm here to tell you that by the end of lunchtime, the t-shirts may be all packed up and gone. So if you want to get a deal on a t-shirt, start buying them now to go to the front desk to pick it up, instant gratification. And remember, everything you spend for the GNU Radio store benefits the project as a whole.
Just do it in the beginning of lunch. Yeah, at the beginning of lunch.
Yes. So as I said, by the end of lunch, they'll be packed up. So if you sneak out the room, you can catch the closing ceremonies here online, and make sure you have a shirt. All right, Josh, I'll turn it over to you for some closing remarks.
I still have one comment remaining about the GSoC thing. So the current 2 students who participated this year, they sent in a video to be played also at this conference because both of them didn't make it. We didn't manage yet to have them played. So either we managed to play them during lunchtime still, or we just send you a YouTube link and include this in the next project presentation or project update. And then everyone will have the pleasure of actually listening and seeing what 2 of our students were able to achieve this year.
We will all be looking forward to it. Go ahead, Josh.
All right. Thank you, Andrej. That is, very, very important program for our community. Let me switch this over. So thank you, everyone, for attending, participating this week. It's exciting to see this many people here still at the end of the conference. So we just want to go through some of the highlights. First of all, feedback. We thrive on your feedback. So things you liked, things you didn't like. I think Marcus has put together this form. So I want to see all these phones up, taking that QR code. It's not a Rickroll, don't worry. Yeah, please let us know. Leave it up for another few seconds here. And we'll email it to all the registered attendees, both here and virtual. So we'll get probably different kinds of feedback on both of those ends. So I want to go through some of the highlights of the conference. It was, for me, this was a great set of talks and keynotes, workshops. Everything just kind of came together, thanks to a great organizing committee and all the people that got involved along the way. So Jack Dongara, he was fantastic, like true pioneer in the field of high performance computing. And then, you know, we learned about the DSA radio astronomy array and Meshtastic, and then of course Dan Boshin's workshops were fantastic. So thank you, Dan, for providing those. Those are, you know, professional level workshops that we were able to bring to GRCon. And then of course Barry and Tom. So raise your hand, Tom. I see Barry's over here running the AV. Tremendous effort. So Wednesday, yet another amazing lineup of talks. Shrihar with the keynote, really on, you know, demystifying science and how he's able to the RF innovations going on at Bell Labs. And we had Trip and some other amazing talks. And Wednesday was really lighter in the ballroom because there was a lot of workshops going on. So we're always grateful for those that are willing to step up and run workshops. We had Neil's Edis RF knock workshop. We had Paul Comet's Basics of SDR, so that was a new workshop. And then we also had, Dan Boshin's and the amateur radio license exam. Do we have any stats on the exam? How many passes? How many? Okay, so five new licenses issued. So that's great. All right, and then Thursday, Phil Erickson from MIT Haystack Observatory giving fantastic overview, and I think there was some connections made in the community about things going on there that impact even other domains. So it's always good to hear people that aren't necessarily you know, doing the same applications, but we learn things that are going on in other fields. And then, of course, Neil Rogers put together a fantastic workshop on how he's using GNU Radio actively in his courses and how that engages students. And then 4.0, again, the ongoing theme, Ralph able to present that and how 4.0 is being developed and GNU Radio used at FAIR. That's always a great tie-in. And Mark with his two talks to related open source projects, SIGMF and IQ Engine. It's great to bring that info into this community. The Capture the Flag, so thank you, Clayton, for running that. That was a fantastic event this year. 111 players. And then Team Aerospace, you guys over here, rocked again this year. So yeah, thanks to Clayton and everyone who participated in that event. And then today, you know, hot off the press is another fantastic keynote, Kristina Collins from HamSci, representing the thing I appreciated most about this talk that was bringing it back to the community and how the HamSci, the citizen science community, can collaborate with the GNU Radio community and some ideas for us to engage better in those areas. So thank you, Kristina. And then also John Moss for bringing all the information about the Oak Ridge SNS particle accelerator and their high power RF equipment there was quite incredible. Our social events, again, one of the highlights of GNU Radio every year. We had on Tuesday night, there was a smaller event on the rooftop, one of the rooftops downtown that SETI was able to run. And then on Wednesday, at the top of the Sun Sphere, and then Thursday, the bowling event. So hope everyone had a great time. You know, heard good things, but yeah, always let us know what you think about these types of events. Now, this event would definitely not happen without our sponsors. Our sponsors make this happen, so we are grateful. Yeah, round of applause. So I hope everyone got to interact in the expo hall. I think that ended up looking great. It was a full house, all the latest equipment and demos going on. Edis Research, NI, always top tier sponsor, and a new diamond sponsor this year, Aronia AG. So they had some fantastic demos and some incredible equipment that I hope everyone was able to check out. Our platinum sponsors, Oak Ridge, who were also very heavily involved in the organization of this conference, and Analog Devices, who enable a lot of the technology for all of these SDRs to work. Yeah. Our gold sponsors, Epic, Peraton Labs, Deep Wave Digital, and ARDC. So round of applause for our gold sponsors. And our silver sponsors, Redwire Technologies, Imona Timms, we have a new sponsor in the education space, DeepSig, B-Cubed, Impulse Space, RFNM, and AnySignal. So round of applause for. And then our patron sponsors, Coherent, Andrej, Timtech, and Doug Forster. Rounds out our list of sponsors. So, and anyone who is sponsored or interested in sponsoring next year, talk to us early. We always want to shape things in a way that it's mutually beneficial and that everyone can benefit from having our sponsors here. Also want to recognize our organizers for this year, Samantha, Barry, Toby, Seth, Andrej, Clayton, Marcus, Neil, and Michael, and also everyone else that helped along the way. So there's lots of people that jump in here and there throughout the year and at the event. So we're grateful to all the volunteers that make this happen. So, yeah. So we're actually, after lunch, we're going to meet over in the Rotunda room and just start casually chatting about next year, some ideas, where we might want to have it. So some years we're able to say where we're having it next year. This year we've waited a little bit, so we're going to start that process, and in the next few months we will hopefully have a better idea where it's going to be next year. But we want future organizers. So if anyone's interested in being involved in this process, all levels of participation are welcome. So, you can be involved full throttle from the beginning, if you like, or you can jump in and volunteer for very specific parts of this. So if you're interested in any way, let us know, grcon, GNUradio.org, or talk to us. So GNU Radio does need you for grcon 25 if we want to make that a successful event. I wanted to make sure we recognize Michael West, who has been sitting out at the registration booth all week. He has, tirelessly worked that booth, and it's a singular Michael this year. So let's see if we can get him in here. Yeah. All right. And one final specific recognition. I want to give special recognition to Barry Duggan. Barry, this event literally would not have happened with Barry. Barry picked up all the pieces. He put together the entire AV setup. He took care of so many details along the way. And we have a special gift for Barry. And I'd like to recognize Barry in a very, very special way.
Thank you. I got into GNU Radio about 5 years ago. I've been an amateur since 1953, and I'm an electrical engineer, computer programmer. So the software-defined radio really appealed to me, and so I started learning about it and reading the documentation and reading the newsletter that said the documentation was terrible. Well, mostly it was because it had a lot of holes in it. They had made a transition from an earlier platform to the wiki we have now. And so I started working on it. I figured out that if I worked on the documentation, I could learn all the pieces of new radio. And one of the things I had to overcome was I had no education in DSP because I graduated college in 1961. DSP was not even thought of. So I had a pretty steep learning curve, but started working on block docs. I have done at least 150, I lost count, and probably closer to 200, and written about 15 tutorials, and got one more planned in the near future. It's adding error correction, forward error my voice gives out pretty quick, forward error correction to my file transfer tutorial. And that's already been tested, and it's ready for me to write it up. So you can look forward to that. Oh, also an interesting note, I wrote an article for QST, the ham radio magazine, and it's been accepted, but it won't come out until around Christmas of 25 because they have this queue of articles they've already got ready to go. So anyway, it's been quite a deal, and I've worked as much as 12 hours a day for the last 6 months at least, just getting ready for this conference. So I'm going to back off a little and do some family time. But thank you for all your support.
So thank you, Barry, for being such an integral part of this community. We appreciate you. All right. So this closes out GNU Radio Conference 2024. So lots of ways to get involved. Lots of ways to email us, contact us, and we'd love to see everyone involved throughout the year. So thanks everyone for being here. Oh yeah, there's breakout sessions this afternoon. Take a look at the schedule, and lunches. Capture the flag at 2 p.m. Anything else? Another Women's Plus social lunch, Rotunda Room, and that should be it. All right, thanks everyone.
The forward error correction project. And I'm going to give you a brief overview of my project and the results. So the point of forward error correction is to detect and correct bit errors that come from the data being transmitted and received over a channel, which inherently adds noise to the signal. So in GNU Radio, there is already